if like we can wait for 3-4 minutes so that
Okay,
it
sure.
it touch 100, so then we will start.
Okay, sure. Thank you.
Yeah. Okay, so Firoja, we can start now. Otherwise, it will be late. So we'll start the session. People will join.
Okay. Sure. So yeah, very good morning to respected coordinators, resource person, and dear participant. So today we are going to start the day 8 session. The course material for the day 8 session already uploaded in the drive. I request you all to please check the drive link for all the course material and related document. Today we are having quiz number 4. It is scheduled as per the timing given in the notification, that is from 2:30 p.m. to 2:50 p.m. We will be having the quiz 4. So with this, we would like to invite Ashish sir for the day 8 session. Sir, please, you can take over, sir.
Okay. Thank you so much, Firoza. Good morning, all of you. So today we have day 8. So today we gonna basically we will study the design flow. Okay, so for a power amplifier or amplifier, so like for any amplifier. So this flow can work for any amplifier, whether you are designing a MIC amplifier or MMIC amplifier. You can basically skip some of the steps, but yes, more or more or less, this is basically will be the design flow. After that, we'll take one example of PA. I'll share the specs, and then we'll try to basically see how we design a hybrid MIC amplifier. Okay, so just to explain you guys what is hybrid MIC amplifier means. Yesterday also I touched upon this topic. So there are basically two ways of making amplifier in RF domain. Okay, as per the application. So basically the two things are, one is MMIC, the other is MIC. So okay, so in MIC you will have discrete device. Okay, so you will have SMD components in your design basically, and you print the layout. Okay, so print layout on some substrate. Okay, so that is there. So what you will do, you basically print the layout of your circuit on a substrate, then mount all the SMD components, capacitor, resistor, inductor, everything that is a part of your circuit. Okay, so you put those SMD components on this layout. You solder them, and you put your discrete active device also, and then you measure it. Okay, so that is basically MIC. Okay, it also known as hybrid MIC. Okay, so what we are doing is we are using all the things separately. We are using device separately, components also, layout also separately. So as you can see here, okay, so there is a lot of human involvement is there, because first the printing will be done. After that, you have to choose SMD components, and each SMD component has its own variations. And also while you are doing soldering, no two MIC can have same basically soldering level. Also, the discrete device that you are using, no two discrete device are basically same. Okay, so variation here is large. Okay, so and also if you want to produce 1,000 numbers, so it'll take time. It take more time to do that, because it involves human involvement. Okay, so there are many automated machines available in the market, but with that also it requires time. So that is basically MIC. But pros of this MIC is that you can basically tweak or tune your circuit even after printing. Okay, so you can change this capacitor and inductor values, because it is there at your hand. Even after printing, you can change a little bit the circuit. You can basically, even you can change the layout also. You can put copper tapes on the layout if you want to add lines somewhere, or you can even remove lines from somewhere also. So this is basically MIC. In MMIC, what is done is everything is basically fabricated at once. Okay, everything fabricated at once only. Here, you do not have that privilege of changing your circuit after fabrication. No change possible after fabrication. Only out like outside the amplifier, if you can put something to make your performance better, that can be done. But inside your chip, you cannot change. No change after fabrication possible. Okay, but if your chip is working, so fabricating 1,000 number is it will be done in one go only. Okay, so it will have a minimum, it will have very less variation also. Okay, so that is basically MMIC. So the S that we are for if you are, but also the size is also very small in of MMIC. Okay, size will also be small, while the size of a hair, the size will be large. But performance, you can always achieve better efficiency, power dissipation. That all will be good with MIC circuits. So you require a foundry service, and also case that Jana sir have told you that in SCL is a foundry. Similarly for GAN, we have a foundry in Hyderabad called GATEC. Okay, so that is also a part of DRDO. So, those people, what they do is they basically fabricate active devices, passive components, everything they will fabricate, and they will provide you the PDK models for that. Okay, process design kit. It includes the model of every passive and transmission lines and active device model, and then you use those model to design your circuit. And after designing circuit, you send your Gerber file to the foundry, and they fabricate the circuit for you. And after that, you will test it. Okay, so that's basically the flow of MMIC. Okay, so before going ahead, I would just like to see if anyone has any question from the past lectures, or from the specifically from yesterday's lecture. If anyone has any question, so I can discuss that just quickly, 5-10 minutes, if somebody has any question, or otherwise we'll go ahead. Okay. Okay. So before going ahead, just the thing that we have faced. Okay. So one of our participant, we will thank to we will thank to I think Dr. Theachni for solving that issue. So she has solved the issue by she has tried many steps. So I'll request her to basically formulate an email in which she will tell that what all steps she has done. Okay, so I think she has tried maybe some installation things that she has tried with 32-bit version and all. So so I just request her if she can make a one email in which she basically stepwise formulate what she has done, and like with which step she is able to resolve the error. Okay, so it will help other participants also to resolve the error that they were getting for minimized function from day 6. Okay, so when we are learning the matching network, at that day some of the participants were facing the issue while running minimized function. So I think the possible solution was that you have to install a 32-bit version for that. In some of the laptop, the 64-bit version is, I might be giving some I would say compatibility issues. So you have to try the 32-bit version. It worked for Dr. Thiachni. And again, I will request her to just formulate one email and send it to EICT Academy, and EICT Academy will then forward it to all the participants, or they can put it as a notification on the drive link. Okay, so there is one question from tomorrow's lecture from Gaurav, is that IMD has unit TBC. You can say that it has a unit of dBc. You can say because you are basically subtracting 2 dB things. Okay, so you're basically subtracting 2. So it is just to I would say it is just to represent that yes, it is much dB down. Okay, so yes, you can IMD has units of dBc. Or any other question if somebody has. Okay, so uh, uh, I think nobody has no further questions are there. So we'll start with the flow. Okay, so coming to the PA design flow. So this is basically what is there is always first of all we have a some specification is there. Okay, uh, so we have some specification that is there for our design circuit. Okay, so this thing you can consider it as basically that specification can be of anything, any circuit that you are gonna design. So you will first have the specification of that. Okay, so it can be for PA, if you say it will be frequency, gain, return loss, power, efficiency, and so forth. P1 dB, linearity, IMD levels, anything it can have. Okay, so you will must have some specification to start with. Okay, then basically if you are designing a MMIC or MICE also, so you first you have to basically select some technology. Okay, so let's say in power amplifier you are having, let's say, the requirement of 20 watts. So you know that with CMOS at that frequency, with which technology we can basically achieve this. I would say the specs. Okay, so you have to choose technology according to that, keeping into mind the all the specification that you are targeting. Okay, so each technology cannot able to achieve all the specifications, so you have to choose it wisely. So basically, you have to have knowledge of these technologies also. Okay, so it is not any big issue. You can always read what are all the capabilities of this technology on the internet, and even if you are selecting some technological PDK, it always provide you a data sheet or some reference manual, something in which all the capabilities are mentioned. So reading that, you can always select a technology. Okay, so you have to basically select the PDK according to your specification. Okay, so then in your technology, there will be many number of devices. So you have to basically select the correct, or I would say the optimum device. Okay, so everywhere the word will be the optimum, or I would say rather good, rather than getting the best device. We require optimum, or rather say good device, so that we will be able to achieve the all the specification, because it might be possible that the device is best with the power, but with just to tell you that as the size of device increases, its frequency, its performance also degrades. So you cannot take a very big device of your technology node that you have taken for very high frequency performance. Okay, so it does not works like that. So you have to basically select a optimum device for that also. Okay, then based on your gain, what is your gain requirement? You have to basically calculate the number of stages that will be required for your PA design. Okay, so and how many number of stages that you have to design to get that particular gain. Okay, so the typical numbers are that with one stage you usually able to get 10 to 12 dB of gain. Okay, so if like let's say if you have to design a 30 dB gain amplifier, so you have to start with a concept that we are gonna design a three-stage amplifier. Okay, so that's how it works. So coming to the fifth part, that is the DC simulation analysis. Okay, so the devices that you have chosen for your stages of amplifier, you will perform DC analysis of that. Okay, you will plot IV curve and various curve of that, and you will see how the currents is behaving, what is the knee voltage, what is breakdown voltage. So you choose your bias point according to that. Okay, so you'll choose your bias point, you make a basically load line you'll put, and you'll choose in which class you are gonna operate your I would say the amplifier, and then you can basically in this you will do all this analysis. Okay, so coming to the S parameter simulation, after you have selected your bias point, at that bias point you will perform your S parameter simulation, which includes the stability analysis also. Okay, so we will see whether it is stable or not with, or if it is not stable, then in which regions it is not stable, or whether we can make it unconditionally stable for all the frequency range. Okay, and then stability network design, that how we gonna stabilize it so that it become unconditionally stable. And then coming to basically while designing stability network, what I told yesterday also, the stability network is nothing but it will decrease the gain. Okay, so we are putting resistor, so if we are using resistor, it will basically decrease the gain. So we have to basically optimize, or I would say rather trade off between the stability and the gain. So we have to find, I would not say a high gain amplifier, we would require a good gain amplifier. So it won't go into unstable region. So that's why we always try to have a good gain amplifier. Okay, so for that, we have to basically see while achieving stability, we do not lose the gain much. Okay, so that's how the things work. Okay, so so after that, basically we need to design a bias network also. I will touch upon this while we are designing, while we're taking example, that what is this bias network design. So just for your understanding here, you guys all know that we have an active device here. So basically to bias this, we will require basically a voltage at gate also and voltage at drain also. Okay, and we have some AC, or I would say the RF signal coming from this side and RF signal going to this side. So basically this is the RF bias design. So what is the issue here is we do not want the RF to lead to this path, because we will be having a DC source here. If some RF will come, if RF will lead to this path, then it can damage this DC source, and if this DC get leakage to this RF, then it can damage this RF source. Okay, so we do not want to happen that. So that's why we need to isolate basically this RF from this DC and this DC from this RF. So how we will do it, in a little while we'll see how we can do it. After that, the design is basically we would say that our device is ready with a stability and a bias network design. Okay, so it, in this block it contains a device with stability and bias network. Okay, so I just want to tell you that this is one of the approach that I am following. Some of the people, what they do is they make it stable. They match it to the 50 ohm, and after that they provide the biasing network. Okay, so you can see many amplifiers which have bias network at the end of the amplifier. Okay, but I follow this way only. We first bias the network with a stability network, and we consider this as a our device. Okay, so this will be our device. After that, the analysis that we have done yesterday. So now this is our device which contains the stability network as well as the bias network. After that, this is our two-port network. So we just have to find out the ZS and the ZL. Okay, so we just need to find out this ZS and ZL. And in case of power amplifier, as we studied yesterday, we can have a S to 2 conjugate match also, and or we can have a optimal impedance we can find out. So So with these two things, we have a difference in the final output, maximum output power. Okay, so we will have some difference, but yes, so this is basically how you will basically design a power amplifier. In power amplifier, you find this ZL using load pull simulation. After that, you basically design this output matching network and see what is the requirement here for a conjugate match, and then you design a input stage matching network. And if it is if interstage is required, then you can match this ZS to ZL of the first stage. Okay, so that's how you design an interstage here. You do not take your ZS to 50 ohm, you just take your ZS to this ZL. Okay, or you can take this ZS to 50, this ZL to 50, and then connect. Okay, so that's how it can be done. Interstage matching will be there if number of stages is more than one. Okay, after that you have to basically do a layout design, and using layout design you have to do EM simulation and basically the optimization of your layout as per EM simulations. And then you will do the sensitivity analysis. Sensitivity analysis is basically that the capacitors, the transmission lines, the inductor, whatever you have used, what are the variation in the values of those capacitor inductors, even in the device also, what are the variations possible. You took all those variation and see how your response can change while you will so if your with those variation, if your response is getting very out of your specification area, so then you will basically desensitize your design for that particular variation, so that even with the variation, you if like after fabricating, even if there are variation, then also you will be able to achieve the specification. Okay, so if you are not able to basically with sensitivity analysis you are not able to achieve your specification, then you have to basically come back to your some stage, so that you can retweak your circuit and come back again and do the sensitivity analysis. So how do we do that? So this is basically that design flow. First of all, as you can see here, we have a design specification here. Following that, we will have a selection of that device. After that, we will basically select which circuit topology we are gonna design. Okay, so then we will do the analysis. Firstly, we will design the circuit according to that topology, and for that we will use the component library, models, PDKs, everything we will use. And after that, we will do the analysis. If after the circuit design, what we are doing is basically we will do the sensitivity analysis of this circuit. If with sensitivity analysis the specs is not meeting, then we again either we will change our circuit topology, or we will again redesign the circuit. Okay, then when the specs is if the layout is fabricate is able is like whether we are able to fabricate layout or not. Okay, so any design rule should not be flawed, so that we will also check that. And after that, if your specs is met, okay, then you otherwise you if it is not met, then you have to go again and you have to choose one of these things, that whether you have to redesign your circuit so that it meets the specs, or you have to basically altogether change the circuit topology. Okay, so you can see here, so before reaching to the final stage, that is mask fabrication, or you can say printing of your PCB layout, you have all this. Okay, so it is a basically iterative process. You have to go through this cycle for like not for like it will not be you will not be able to do it in a one go. Okay, if you are trying the power amplifier for the first time, you have to basically follow this path like it for like 3-4 times you have to follow. So that's why a general typical design cycle for a power amplifier is vary from 2 to 4 months, and it can vary up to 6 months if you are if you are like basically a new designer. Okay, so if for an experienced designer, it take around 2 to 3 months for design MMIC amplifier, and for MIC amplifiers, it take around 2 months, 1 to 2 months, because in MIC amplifiers, as you know, we have to just print the only the basically transmission lines, and SMD components we are putting outside the from like SMD components we are putting. So in that, design rule check and layouts does not play so much role. But while you are designing MMIC, you have to do the EM for whole circuit, and with that, the you want the things to be very perfect, because the fabrication cost of a MMIC is very high. So you just want to be double, triple, four times sure that yes, there are no, I would say, no bug that is there, so that your chance, the chance of the circuit performance becomes high. Okay, so that your circuit will perform good. So you want to be very sure for that, because in MMICs the fabrication cost is very high. So you can consider the one wafer run cost of a GAN is in crores. Okay, so 1 crore, one wafer run, and in one wafer you will get only basically 200 to 400 devices only. Okay, so that's basically that basically MMIC is that much costly. Okay, so before fabrication you want it to be, I would say, like four times surety. But while we are designing MIC, it costs basically we just have to print the PCB on a given substrate, and that costs around like in thousands, 4,000, 5,000, depending on the area of your PCB. And the cost of substrate is around like you will get I would say A3 size of substrate in like 10,000 to 20,000 of range. Okay, so you can see this, it is very cheap. But yes, but the variation while making the designs is more in MIC and very less in MMICs. Okay, so that's basically the design flow that usually we used to follow while designing a power amplifier. So so coming to the example of, okay, so basically we are targeting a sub 6 gigahertz band of 5G application. Here the frequency that we have chosen is 5 gigahertz with a basically we require a 100 megahertz band. So it should be from 4.95 to 5.05. Okay, so basically our desired band is this much, but we have taken 50 megahertz on both the side as a guard band. So our basically we will design it for 4.9 to 5.1 gigahertz, so that if our response shifts a little, so it should the original spec should meet. This is basically the guard band that we have taken, and the power that we require is the 20 watt. Okay, and the gain we require is 10 plus minus 1 dB. So this means we can achieve it with the single stage only. Okay, so it might be maybe greater than 10 dB also. Okay, so for then you have to take two stage the power amplifier design, but right now it is just 10 plus minus 1. And I already told the return losses are always required to be better than 10 dB. So these are the basically general specs. You will always see specs for return losses in this range only, 10 to 12 dB only. But sometimes in some papers you can see if a power amplifier is of very high power, okay, very high power amplifiers, they have this output return loss very low. Okay, so why it is very low? Because you know that with S22 conjugate match you get a good output return loss. Okay, so you will get a very high output return loss for a S22 conjugate match. But for achieving high power, what we are doing is we are doing a power match. Okay, so for achieving high power we are doing power match. So this power match, if it is power match is very far from, okay, so this power match is, if it is very is not is is not equal to S22 conjugate and it is very far from this, then basically this output return loss at small signal will be less than 10 dB only. Okay, so for a power amplifier case, output return loss are generally not better than 10 dBs. If you are basically targeting very high power of that technology node. Okay, so this 20 watt is easily gettable from the GaN device. With the S22 conjugate match also, the device that we have chosen, we can achieve this 20 watt easily. Okay, even with the S22 conjugate match also. Okay, and the efficiency that is required is 40%, and this is a like it is very easily gettable from GaN technology. Okay, so that is basically the specs that we have to met today. So we will make a power amplifier using the that will have these specs only. Okay, but so coming to the selection of device, basically what we have to do is we have to see what type of application we are targeting, what is the gain requirement, what is the power dissipation, current specifications are what, frequency range of operations are what, constraint on chip size and these are basically all the points that you have to cater while you are choosing the devices. That I have listed down all the points, but here we have only some of the specs that we have to met. But for that, we have chosen basically a GaNHAM device here, which is of like 35 watt, 30 to 35 watt it can give. You can see this device. You just write Cree EGH 55030F GaNHAM device, and you will be able to find this device PDF on the internet easily, and you can see that it can even deliver up to 35 watts. I have used that device and it can deliver up to 35 watts. Okay, so and the basically bias voltage of this device can be go up to 35 volts, but we have chosen it in to be in the safer range, so that it does not, while we are driving the power amplifier, the swing of voltage swing that we have seen yesterday, right? There will when you basically apply VG, when you apply P in, your drain voltage swing will there will be a voltage swing on the drain also. So this voltage swing here should not go below breakdown. Okay, so if it is going below breakdown, then it will damage. So that's why its breakdown voltage is around like 100 volts. So we always choose the bias voltage for our device as the breakdown voltage by 3. Okay, so anything below V breakdown by 3, we can choose anything below V breakdown by 3. We do not go above V breakdown by 3 voltage. Okay, so in this case, that voltage comes around 35 volts. So we are basically choosing 28 volt of operation. So it is quite standard voltage of operation also in today's world. This many of the circuits uses this drain voltage only. So just to be in sync with those voltage requirements, I have chosen 28 volts. Then the bias current in datasheet, if you see, you will find a quiescent bias current that will be at minus 2.8 volt, and it at this VG it will be having a bias current of 340 milliampere. Okay, and for our designing the circuit to meet the specification, we are choosing a deep class AB operation. So by deep class AB, what we mean is basically we have this way we have basically IDV, basically IV characteristics are like this. So for class A, it should be like basically it should be in the middle. For class B at the cutoff. So class AB is that it will be very near to class B. So you can say this as deep class AB. Okay. So if it is near to class A, it will be only class AB we used to say, but deep class AB means that thing. Okay, so that it is very near to class B only. Okay. So this is the device that we have chosen for our design. Okay, so and this is the substrate. Okay, so this was the substrate that is available with us So that's why I have chosen this substrate. Okay, so you can choose any other substrate also that is available at your end or at your place, whatever substrate is available for this. But for the particular design that we are gonna do today, we have chosen this substrate. That this substrate is basically a Rogers Artidoroid substrate, which has this number 6035 STC substrate. Its basically dielectric constant is 3.6. Its thickness is 20 mil, which is basically 0.508 micron. Sorry, okay, or 508 micron. Okay, and if you see the data sheet of a substrate, you always find like if it is a microstrip is like this. This is ground, and you have a metal here with a W width. So this is that metal thickness T. So this metal thickness T is always given in ounce. So now this ounce is a unit of a gram, but what is meant by 1 ounce is that in an area of a one 1 inch. Okay, so 1 inch by 1 inch area, the 1 ounce copper is spread uniformly. Then what will be the height that you will get? So you know that density of copper is constant. So when you basically putting the mass over an area, then basically area. So density is basically nothing but mass over volume. So you have the density, mass, in volume, you have area into height. Okay, so this height you can find out. So for 1 ounce of copper, the height is 35 micron. I just want to tell you that when you are seeing a data sheet of any substrate, you might find the thickness of the metal that is on the top or at the bottom. It will be always be mentioned in ounce, and 1 ounce will be equal to 35 micron. So this will be the thickness of metal. Okay, so and similarly, if it is half ounce, then it will be 35 by 2, and if it is 2 ounce, then it will be 70 micron. Okay, so that's how you have to find out the thickness of metal. Okay, so if any doubt is up to this point, you can ask. Otherwise, we'll go ahead. Nothing much that I have told till now. But yes, if any question about specs or substrate or device, anything that you want to ask, you can ask now. I will. Otherwise, we'll go ahead with the design flow. So, uh, so basically, today, so they will be using our tool mainly. Okay, so there will be not much of slides, but yes. Okay, so why GAN, sir? Because basically, I would say for this example, I was able to easily get the data sheet of the GAN device. I was not able to find the other devices. That's why I have designed the example in that way. But why GAN? If you see such kind of specs, it is that at this high frequency, that is basically at 5 gigahertz, getting 20 watts of output power is with GaN only you can achieve it. Okay, with CMOS and even with gallium arsenide, getting this 20 watt is very difficult. Okay, you can get it, but these are very difficult specs to meet with other technologies and very easy specs to meet with GaN technology. Okay, so that's why I was saying that for 5G, GaN is getting very high boom because to get all the specifications of a 5G system, the technology that can meet those specifications is GaN technology. You can read it on internet that why GaN. Okay, why GaN for 5G? You will find many of the literature for that. Okay, so there is one more request. Rather, it is that can you please tell how the circuit hardware is tested? Oh, so that will itself be a very, I would say, a 5 day workshop that can be, I can conduct 5 day or more than 5 day workshop for that only. But yes, I will tell you in very short details if I have time. If I left with some time, then I will tell that how to test the hardware. Okay, so in a very short time I will tell that, but just I would say that that itself a topic. Measurement is also a very crucial part in RF circuits. Okay, so you just cannot do measurements very easily. So it itself a very a wide topic. Okay, so but okay, I'll tell you some basic measurements in a very quick way. I will tell that how you can measure it. Okay, can you please repeat of the output return loss 10 greater than 10 dB is achieved. So Saptrishi, with output return loss, what I meant was is that so basically the question from Saptrishi is that how the return loss of greater than 10 dB is achieved. So basically, what I meant with that is when you are designing a power amplifier, yesterday we have learned that there are two techniques of making an amplifier. Okay. Okay. There are many other techniques also, but we have studied two techniques that we have to find out ZS and ZL. Okay. So ZS and ZL can be the simply the conjugate match of your device impedance also. But for a power amplifier to achieve maximum power, what we require is a optimum impedance that will be provided when it is matched to your device, then it will give the maximum power, and that is because there exists non-linearity in your device. Okay, so when you do a power match, so that power match can be very far away from your S22. Okay, so if S22 is very far away from your power match, then the return loss. So it means that you have to play a trade-off. So either you can achieve a maximum power of your device by doing a power match, or you can do a conjugate match, S22 conjugate match, so that you can get a good return loss. But at that point, at that conjugate match, you will not get the maximum power. So basically, you will choose in between so that you will get a return loss also and you will get power also. So that's why, as you can see, the requirement was just 20 watts, but I have chosen 35-watt device, that the device that is able to give 35 watt of output power, so that with S22 conjugate match also we will be able to get 20 watt of power. Okay, so that's how we will achieve output return loss better than 10 dB, because in a communication power amplifier you always require return losses of output, basically output return loss to be better than 10 dB only. Okay, so that's how we will try to achieve output return loss better than 10 dB. Okay, I hope it is clear now. So going ahead, this I think I have already taught you. So if how to find a number of stages in a power amplifier. Okay, so basically this is a single stage. Right now what we are targeting, so what we have an active device which includes the biasing network and the stability, and we have to match it to basically conjugate and the optimum impedance of the output network. Okay, so this is basically single stage, and if it is basically two stage, so we will have a device 1, device 2, this will be device 2, and we have the output matching network, then we will do the interstage matching network, and then we will do the input matching network. So just remember that while we are designing a power amplifier, we will always start from the output matching network and we goes towards the input matching network. So any number of stages of amplifier you have, you always start from the final output network and then you go with the other matching network. So you will go like in this direction you will go. Okay, so from right to left you proceeds. Okay, so we'll come to basically the tool implementation of the power amplifier. Okay, so we will see, we'll go step by step. Okay, first of all, we will see the characteristic of our amplifier, what we have. Okay, so what are the characteristic of the power amplifier? So I have provided you guys with the S parameter file of this device at bias minus 2.8, VG equal to minus 2.8. Okay, the VG is equal to minus 2.8 and VD equal to 28. Because we cannot include model right now in this tool, so we are using the S parameter file. So that S parameter file is created at this bias. Okay. So they have somehow measured, you can think of it like that. They have somehow measured that device, and after that they have de-embedded all the other networks, and they are given the S parameter at this level. Okay. So that this device, if you see on the internet, it will be in a package like this. Okay. So this will be its package. It will have one cut on here. Okay, so this is basically gate side, this is basically drain side. Okay, so so the S parameter that we have got will be at this end. Okay, so they have measured it, somehow they have measured it, then they have de-embedded all the pins and everything, and then they have basically I would say they have de-embedded all the points, and they have given the S parameter at this level. So right now we are at this level of I would say our device. So our device has S parameter up to this reference plane. Okay. So we first analyze the device. Okay. Obviously we cannot do the DC analysis with this tool, but yes, we have S parameter from the data sheet. So we will use that device parameter, and this is there in this file. I hope you guys able to run this file. It is not like corrupted like last time. It was corrupted, so that's why I have sent it through mail only this time. So I would just like to see your comments if you are able to basically run this first two blocks, and it is giving this thing device SPARAM 1 to 6 gigahertz. So everyone is able to run it, and no one is getting error. Okay, or maybe if somebody is able to run it properly. Okay, so that will make that will give me confidence that yes, this S2P file is working now. Okay, so if somebody can tell whether it is working or not, I'll give you 2-3 minutes. If you have not downloaded the file, you just download the files and just try to run this first one underscore PA, the first two blocks. Okay, just make it sure that you keep all the file in the same folder only. Okay, do not keep this device as param PA in some other folder and the other files in some other folder. Just keep all the files in the same folder. Okay, so thank you, Gaurav. Gaurav is saying yes, it is working. If 2-3% can say okay, worked. Okay, thank you. So now this S2P file is working. Last time I have sent it through some other form of media, but I think we can only send this S2P file through Gmail only. Okay. So now you can see we have basically called the network. In this, what we have done is it might possible that your S2P file that you have created, it might be on some other frequency range, or maybe it has some other frequency points. Okay, so those frequency points can be like so maybe those frequency points, maybe it will be like 1 to 6 gigahertz, but they will be like 1.04, 1.08, and 1.2, something like that it goes. But what you are defining is maybe you are defining like 1 to 1.1, 1 to 1.2, 0.3. You are basically increasing with one data. So you just want everything to be with the same frequency units. Okay, so that's why for to make that, what we do is we just basically import the network, as we studied in the tutorial that how to import a S2P file. After that, we just write dot interpolate underscore frequency, the frequency that we have defined. Okay, so this is what we have defined. If we do that, it will basically interpolate the S parameters of this whatever the S parameter we have in this S2P file as per on the frequency points that we have defined here. Okay, so then we can use this frequency for our further components. Okay, so then it will be easy to work on. Otherwise, it always gives error. Okay, it might possible that this S2P file has only 501 points. Okay, it does not have this 101 point from 1 to 6 gigahertz. So that will create error. Okay, while you are running the codes uh, ahead. So that's why we have to make sync the frequency for all the components. So that's why we have used this dot interpolate underscore frequency. I hope that this thing is clear to you, that we require frequency points to be in sync with all the things. If you use the MATLAB files, okay, if you are familiar with the MATLAB, you know, while operating on the matrices, what you require is to have so what you require is to have the matrix size to be same if you are operating on those metrics. Okay, so that is basically the same that what we are doing here. Okay, so we have a question here that can we change 1 to 6 gigahertz to 3 to 6 gigahertz, or it is fixed for particular S2P file? No, it is not fixed, Gaurav. You can change it to any frequency range. I have chosen it from 1 to 6 gigahertz. You can take it from 2 to 4, 3 to 4, 4 to 5, 5 to 6, even 3 to 6, 2 to 6, 1.5 to 6, 1.5 to 5.5, any value you can choose. Okay, I have just taken it randomly, okay, just to see the response from 1 to 6 gigahertz. Okay, but you can choose it to 3 to 6 also. It is up to you. But just to make sure that you use this interpolate frequency here, so that it works well in the further part of the codes. Okay, otherwise what will happen is the mismatch of the network will appear, and that will cause harm that will cause error while you run the code. Okay, so first of all, we will plot all the S parameters. So we are not interested in S12 because that will anyway the isolation only. So we are basically interested in S21. What is the gain of the device basically, and what are the S11 and S22 values? Okay, so I have plotted it in dB. So you can see here we have a very low gain of the device at this frequency. Okay, so all the gain that we have to achieve is by the matching only. Okay, from GS and GL only. Okay, so that what we have to achieve by making an amplifier. Right now at 5 gigahertz, if you can see here, the gain is like around 1 dB only. Okay, so 5 gigahertz, the gain is only 1 dB. And if you can see the S11 and S22 part on the Smith chart, okay, so you can see here, this is basically the frequency spread of the S11, and this is the sorry, this one blue one is of S11, and this orange one is for S22. Okay, so these are basically the impedance level of the device at different frequency, starting 1 to 6 gigahertz. So it will move like this, 1 to 6 gigahertz. Okay, so it have the impedance lies basically in this part of Smith chart only. Okay, so this basically shows the how the impedance of the transistor is changing with the frequency. So you can see that here. With this, you will be able to find that information. Okay, so after that, after just seeing this all thing, everything is in place. We can see here the S11 and S22 for all the frequency lie within the Smith chart. Okay, within this R equal to 0 circle. So that means this mod S11 and mod S22 is less than 1 only. So we do not. So basically, what we have to check whether this device is stable or not for all the frequency range. Okay, why all the frequency range? But as we are making the amplifier at 5 gigahertz only, so why we want the device to be stable at all the frequency range? It is because that when we apply the bias through a practical DC source, so that practical DC source is never be constant. It always contains some ripples. So that ripples is always correspond to low frequency range. Okay, so that low frequency range can be picked up by the device. A low frequency signal, this low frequency signal can be picked up by the device, or it might possible that you will be having a transmission line, and you know that we have some ISM bands in 300 megahertz range. Okay, so this can act as an antenna, and it can take this signal from the air or from maybe from the surroundings, and the device that you are using, it can basically goes off your device. Basically, it will make your device unstable, and it will burn off eventually. Okay, so that's why we want unconditional stability for the whole frequency range domain that we are considering. Okay, so for that, what we have to do, that we have to first check whether the device is stable or not. Okay, so first of all, our first task is this only, that whether our device is stable or not. So how to check that? Yesterday we have seen one thing, that yes, by this we can check. So can somebody tell which test was that, from which we can tell the device is stable or not? So can somebody answer that which test, from using which test we define that yes, that the device is stable or not, and what are its condition? Okay, so do not look at the slides. Just give me the answer. So it will it will give you also the confidence. Okay, so K, delta, or mu test. So what are the basically condition on K? Delta should be less than 1. Okay, K should be, sorry, Saptarishi Ghosh is saying K should be less than 1. I think you are seeing the slides. Yesterday I have told you have to correct this thing, that K should not be less than 1. K should be greater than 1. Okay. So for device to be stable, K should be greater than 1. Okay. So in the slides, it is written that K is less than 1. That was mistake. So you just correct that K should be greater than 1 for the stability. Okay. So we will basically plot that stability factor. Okay, so we will calculate that this S11, S22, we have defined it. We stored it in a variable. Then we have calculated delta S11 S into S12, and then we calculated K1, K2, K3, K4, and then we have calculated basically the absolute value of all the things, and then I would say the final K value that we calculate through this, and then we have plotted the K value. As you can see here, at this frequency range, beyond this frequency range, like below this frequency, the K value is less than 1, but at 5, our K is greater than 1 only. Okay, so that means this means that K is basically less than 1 for lower frequency. I told this thing to you yesterday also, that for all practical devices, the K is less than 1. Basically, devices are unstable for the low frequency range only. Okay, at high frequency, it eventually becomes stable. So basically the device is having a high gain. Okay, so you can see here at 1 gigahertz, it is having a gain of like more than 17 dB, and at 5 gigahertz, it is less than 1 dB. And if you go beyond 1 gigahertz also, the gain will rise like anything. So maybe at 500 megahertz, the gain will be like 25 dB also. So with high gain, the stability will be less. Okay, so it will be tending to unstable. So that what we can see from the K value also, that yes, our device is unstable here. So basically we have to compensate the gain. So we do not want this much high gain even at the low frequency also. Even if you are designing amplifier at 1 gigahertz, you will not target this 17 dB gain, because with this 17 dB your device is unstable. Okay, but we have to make it stable at this frequency range also. So one of the way is that you just see the stability circle. So I have plotted input stability circle using the formulas that I have taught you yesterday. Okay, so you can check this code, that how it is implemented, those formulas that I have implemented here. Then using a function, I have basically using a for loop, I have called this function again and again, and just plotted this, I would say this circles. So you can see here, so how nicely this tool plots the stability circle. This stability circle are at input. So you can see here this stability circle is 1 gigahertz and it is going ahead. So this is 1.5, 2, 2.5, 3, 3.54, 4.55, 5.56. So you can see here as the k value is becoming greater than 1, the stability circle is going out of this Smith chart. Okay, so for this frequency range, it is already unconditionally stable. But for 1 gigahertz, there are some impedance values for which the device is not stable. And you know that the conjugate match requirement that we require is falling in this area only. Okay, so basically we need to we want this input stability circle to be moved out so that we have an unconditional stable condition for all the frequencies. Okay, so coming to the output stability circle, again the same thing. Here we have a larger area of impedances that will become responsible for the unstable region. And you can see here this is again 1, 1.5, 2, 2.5, and that's how it is going. And the other stability circle are out of the Smith chart, but for this frequency, we are basically having the impedance ranges that is making it as unstable. Okay, so that's how you do the analysis. Okay, so we have seen that yes, our device is unstable, so we have to design some way. Okay, so that it becomes stable. So yesterday I have introduced to you the fact that we make the device stable by putting resistor at gate or drain. So for while we making a power amplifier, we always put resistor in series to our device. Okay, so like this we will put. So, but with putting this resistor, okay, so why we have put this resistor, it will basically kill our gain. Okay, so it will kill our gain at all the frequencies, and we have already very low gain at 5 gigahertz. Okay, at 5 gigahertz we have very low gain already. So what we want is that this resistor, okay, so it will kill the gain at lower frequency. It should kill the gain, but it should not kill the gain at higher frequencies. Okay, it should not kill the gain at higher frequency. Even it should not kill the gain at higher frequency. So that is what we desire with our stability network. Okay, we want to kill the gain at only at basically at the lower frequency ranges. So what we do that for that what we do is we have to put a network here. Okay, so basically I would rather ask I should have asked you guys, but just I want to show you how we will think. Okay, so we need a network here basically. Okay, so that will be act as a open. Okay, so it will be like a switch here. So what we want here is like a switch here that for low frequencies it will be open. So all the current will pass through this so that it can attenuate. The resistor can attenuate those signals and we have a less gain. But for higher frequency, this will be short so that all the signals will pass through this and we won't see the effect of resistor here. Okay, so this is what we require. So for that, what we want is basically we want a response like this. Okay, so it should not basically for lower frequency it should be I would say open path, or I would say it would have a very high loss. Okay, and for low high frequency path it should have very low loss. So it is basically a high pass filter sort of thing. So for that we know we will put a capacitor in series. Okay, so in this path what we found a solution is that we can put a capacitor in basically that will become in parallel with resistor. So it will serve our purpose that it will become open for the low frequency signals, and it will become short. It will act as a short for the high frequency signals, so that the resistor won't kill our gain at higher frequencies, and it makes the device stable at lower frequencies also. Okay, so that is basically is called a parallel RC network. So this is basically our stability network for this device. Okay, so this we have seen, that is basically there. While choosing, I'll come to the next slide. Basically, next notebook. You can also open that. That is 2_P_A_ with stability. Okay, again the same code is there. The one we were having in the 1_PA1. The only thing is, again, you have first imported your device as parameter here. Okay, so sorry, I have to run the first block first and then the second. Okay, so you can see here, I have run this block. After that, we have basically designed this circuit. So through this, all these lines, I think by now you all know the meaning of all these lines. If you see it properly, you will be able to recognize that I have basically with the S parameter files. So with the S parameter of device, okay, here what I have created is I have created a parallel RC network here. Like that, I have created one RC network here, and you can basically change the value also. But what I have found with some tuning and with all the trade-offs that we can found. Okay, so that's how I have reached to these two value, 100 and 1.2. What you guys can do is you can create that tuning circuit type of thing, in which you can tune the value of R, and you can tune the value of C also, and see the response. Okay, so which response you have to see? You have to see the value of K and S21, and you have to see the K should be greater than 1, and this S21 will also be high. Okay, so this should also be high. So for what values of this RC you have to find this, basically you have to make trade-off between these two. So you have to make sure that K should be greater than 1 only, and S21 should be as high as possible. Okay, so whatever the best solution you can find out, you have to find that. So you can basically tune those values. The other thing is also that I have chosen 100 here is because in the market, if you go to buy like power resistors, basically of the power handling that we require is should be greater than 1 watt. So that is what is required. So what I was getting is the 100 ohm resistor only. So that would become my limitation, and that's why I have fixed it to 100 ohm. And then I have just tuned the capacitor value to basically achieve these two specs. Okay, so at this point of time, we want to basically play with these two things, so that we also achieve K greater than 1, but our S21 should not be very low. Okay, so we want S21 to be also high. Okay, so that is basically the target while choosing these two values. Okay, so as of now, because that cannot be done in the 4 hour time, so that's why I've already done it for you guys. So what why I found is 100 and 1.2 puffs. Okay, so I am again saying it. This is it is not like that. It is an optimization problem, and you can choose only these two values. Okay, so it can be anything. It can be 52 puff also, 51.2 puff also. It depends on you. At what point you are choosing. So right now we have choose 100 and 1.2. Okay, so with this I was able to achieve the specs. But if you can try it with 51.2 also, and other things also you can try, but just make sure that K should be greater than 1. It should not flout this statement. Otherwise, putting RC will not help us. Okay, so what we want is that K should be very very greater than 1, even at least for the lower frequencies. Okay, so that is basically that what is desired from the stability network. This is basically what is the most important part that what we want by putting this RC. Otherwise, all the purpose of putting RC will lost. Okay, so after so if we run this, okay, so I think So now if we run this code, so you see here, uh, so I have just do it with for the comparison also. So you can see here that yes, this was our device S parameter. This blue one, the initial that was without stability. Okay, so this your S parameter device S parameter without stability. Okay, and you can see we have successfully basically killed the gain at lower frequency more and very less at higher frequency. It will kill, okay, so it is basically killing, but it is not killing that much that it is killing at lower frequency. Okay, so that is the with the physical practical scenario, that because the capacitor is not acting exactly as short, it will offer some impedance, and the resistance will also be some impedance. So what impedance it is offering, according to that, it will act as a divider sort of thing. So some part will pass through resistor and some part will pass to capacitor, but most of the, I would say, the power will flow through capacitor only, but some will leak through resistor also. So that what we are leaking through resistor will basically decrease our gain. Okay, so at lower frequency, the power that is passing through resistor will be more, so our gain has decreased more here. Okay, so this is basically the thing that we are trying to achieve here. Okay, and you can see the other parameters also, that how S11 and S22 is basically changing. Interesting thing to see here is that S11 is changed here. Okay, but it okay, so I have what we have gained through this RC network. What we have gained here is that initially our S parameter of, okay, so without stability, the S11 was here. Okay, so this was our S11 requirement, impedance requirement without stability. Okay, so but this is very far from our 50 ohm match. Okay, so this was very far. So if you try to design a matching network with this, it will be very narrow band. Okay, so it will be very narrow band. Okay, so what with RC network we have achieved also is the matching. Okay, so this response has shifted to this area. Okay, so it is basically higher impedance. So basically we have moved towards the 50 ohm environment. Okay, so with this stability network, we have basically achieved some sort of matching also. Okay, so the primary, I would say, the task of stability network is to provide stability only. But with this stability network, we have basically moved towards the 50 ohm environment also. Okay, so matching this impedance to 50 ohm and matching this impedance to 50 ohm. With this, we can get better bandwidth rather than matching this impedance to this area. Okay, so with stability network, we have sort of achieved matching also. So while choosing value of 100 of basically resistor and capacitor, you can look at the S11 impedance requirement also. So if it is coming very near to 50 ohm, then those value of resistor and capacitor are like favorable for us, because after using that, the matching will become easy. Okay, so it will help us to achieve the matching with the less number of components, and it with the basically with a greater bandwidth also. Okay, so basically we have seen that yes, with RC stability, parallel RC stability network, our primary task was to achieve stability. So we will see later that whether we are able to achieve stability or not. But we have seen that as a byproduct, we have achieved some matching also. Okay, so we have achieved uh, some matching part also we have achieved. Okay, obviously we have put a resistor there and a capacitor there also. So basically we have introduced some matching also there. Okay, so but with stability network, uh, so that's how I was saying that you can, while choosing value of RNC, you can look at this factor also. Okay, so you can look S11, S22, sorry, S21 and K factor. Okay, S22 won't change much. Okay, so we will see S22 also. So basically, S12 of this device is not very high. Okay, so that's why putting anything at the gate won't change basically anything at the output. So we can see it will change a little because S12 is not exactly zero, but it won't change it very much. So you can see here with stability and without stability, the impedance requirement is basically the exactly the same only. Okay, so it is not varying much S22. So that also shows that S12 is not very high. If S12 was high, then it was putting RC at the gate will would must been have been affected the basically the output impedance also. Okay, so that is there. Okay, so now we will see the again the stability factor, the same code we have. Okay, so we have calculated the both. This was the initial k value of the transistor, and now after stability network, we have basically achieved. We have made the k very high at the lower frequency. Okay, so you can see that even at the lower frequency, it will not go beyond zero, beyond less than one. So it will be like uh, easily, I would say, it is very much greater than one at lower frequencies. Okay, and we had tried it to be kept as low as possible at the higher frequency. So you can bring it down more at this levels also, but I would say this will come with experience, that at which level you have to keep. It is not like that you always try to achieve this form of k factor only. Sometimes people try to achieve, like at lower frequency they try to achieve higher value, but at the frequency they are designing the circuit, they try to achieve the value of k as close possible to 1 as possible. Okay, so they always try to get the value of k as close as possible to value of 1 at the desired frequency range. Okay, let's say suppose this is 1, so then they will try to achieve the curve like this at 5 gigahertz. Okay, so they will try to achieve like that also. So that basically depends. So maybe that's why I have told that you have to sometime do 2-3 iterations for before finalizing your PA design. Okay, so right now we have chosen 101.2 value. With that, this is the k value for frequency range. It is coming like that. And if you see the stability circles, you can see here now all the stability circle have gone out of this Smith chart. Okay, you cannot even see the output stability circle. There are no circles you can see here. Okay, so everything is gone out of the Smith chart. Okay, so you have just able to see one or two circles here. So everything has gone very far from this Smith chart. So you can say that yes, our device has become now unconditional stable for all the frequency range. Okay, so that's how we have achieved stability, and we have seen with this stability network we have achieved some sort of impedance match also. Okay, so that is basically the stability network. Okay, but the issue here is you just cannot connect R and C like that. Okay, so you just cannot connect R and C like that at this frequency range. Okay, so you cannot use those resistor that used to have a long wire here, and a capacitor of this sort, and you just connect these two wires. Okay, so you cannot use those wires. The SRF of these type of resistor and capacitor is very low. It will be like below 1 gigahertz also. It might be below 500 megahertz also. Okay, so you cannot use these type of resistor and capacitor. You have to use some specified resistor and capacitor that are formed in form of assembly components. Okay, so you require that sort of basically components. So you cannot basically connect these two directly. Okay, so you have to have some pad there. Okay, so that you can solder R there and C there like this. So that pad you require. But if you are introducing pad there, so so these pad also need to be simulated. Okay, you cannot just put pads anywhere, and you do if you do not consider those pads in your simulations, then your frequency response will change a lot. Okay, so your response will can change. It can go havoc also. So you have to basically include each and every transmission line that you are using and considering the device package. Okay, so it will also have a pin. Okay, so it is also having a pin, so you have to put pad for that pin also. So first of all, the first most important thing is to put pad for this pin. Okay, so that you can easily solder this pin on those pads, and you have to include those pads in your simulation. Okay, so the next thing what we are gonna do is to include pad with the device. So how to do that? I will just quickly look. I'll quickly show you those steps. Okay, first of all, we have. I think you guys have understood that we have to put pads. Okay, at the device and we have to put pad. Okay, so again I will draw. Just uh, my drawing is not that good, but still I am just trying to manage. Okay, so this is basically the device package. That's how it looks. So what we want is some pad there. Okay, so that we can solder our device on those pads. Okay, this pin we can solder on those pads. So if you see the device dimensions, the dimension of this pin. So the length of this pin is like around 1.2 mm, and this is also 1.2 mm, and this is also 1.2 mm. Okay, so this is basically the size of the pin that is there. So basically what we will do, we will make a pad a little broader than the pin size, so that we are easily able to solder the device on this pad. So what we have done here is we have basically designed this pad with the transmission line, with the microstrip transmission line. Okay, so that will act as a transmission line only. Okay, so at the bottom that will be having a ground, and at the top if you are having a pad, so this pad is basically nothing but a transmission line only. Okay, so what we want is a transmission line. So basically this is the substrate that we are using, that 6035 STC substrate. Its loss tangent is 0.013. Okay, so first width we have defined as 1.5 mm. Okay, so our requirement was 1.2, so we have taken like around point 1 point 125 on both the ends, and we have basically in totality we have taken 1.5 mm, so that 1.2 mm can be kept easily on the pad. And with this we have defined the microstrip line. Okay, with this width we have defined the microstrip line, and using this microstrip line, we have defined two lines, line 1 and line 2, with the length of 1 mm. I think, okay, so I think I have the pad size, I think that pad size is 0.8 mm only. Okay, so that's why I have taken, so basically this width is basically 1.2. Okay, but the length here is only 0.8 mm. So that's why we have taken 1 mm here. Okay, so this 1 mm will be the length of the. So these two lines basically making the pad of the device. The drain, this will be the gate pad, and this will be the drain pad of the device. Okay, now what we have to do, we have called the device here. So this will create that network of the device. After that, what we have done is that we have defined the stability network, and then what we have done is basically uh, we have just created the device now with pads. Okay, so with these lines, with this this thing, we have created device one from device that is along with the two pads are here. Okay, so this is with along the two pads are there, and then again the same way we have used this device one, and we have created a stability network there. Okay, so that's how we have created the pad for the device. Okay, so this is the way, that's how we can include the basically the pads on which our pin of the transistor will rest. Okay, on which we will solder those pins. Okay, so we have to include those transmission lines, those pads into our simulation also. Okay, so at this frequency ranges, at RF frequency range, we have to include each and every transmission line that we are putting. We cannot basically leave anything assuming that it won't affect. Okay, and we will just put it in our layout. So we have to basically include each and every transmission line in our simulation only. So okay, so we cannot omit any line. It might possible that those lines won't affect our response much, but we in totality, when those lines come into in contact with other transmission, then it can might affect. Okay, or it might not affect also, but you should make it a practice that you should include each and every transmission line in your simulation at your simulation level only. Otherwise, when you try to put those transmission line while making the layout, because you have to put register or the device, then those transmission line might cause might maybe shift or maybe totally degrade the performance that is expected from your, I would say that the amplifier design. Okay, so while after fabricating, it might not work the way you are expecting it. So that's why we have to take into account the each and every transmission lines. Okay, so again, I have missed the first block to run. Okay, so you have to just run the first block, then you can see all. I just run all the blocks, and you can see here. So our now our basically S22 have shifted a little. Okay, so it have basically included this those transmission line also will act as a basically it is nothing but a impedance matching only. Okay, so it will act as a shift in impedance. Okay, so it is basically shifted the impedance from this point to this point. So our curve of a paired device was this, and with this pad our impedance level is shifted. So you can see that if we have not included the pad in simulation, this shift we won't be able to, I would say, characterize. Okay, otherwise, and this can give a basically failure of our design. Okay, and you can see here the basically this S11 also, and this is also might have been shifted a little also. Okay, but here I have not plotted the paired device with stability. This was our device only, and this is with the device with pad and the stability network. So this is that response. It also might have, it also must be shifted from the device with stability network, and you will get this response. And you can see here. Okay, so if you compare, you can do it at your end. If you compare this network, this is basically a device with pads network. Okay, so this is basically device with pad with stability. Okay, so gain here, if you see the gain here. Okay, so you will found that it is a little higher than what we were having with only device with stability. Okay, so that you can see easily here that yes, our gain is have crossed a little at this edge. Okay, so that's why at this point of time, also you can re-optimize your RNC value, so that because you have included something before between device and between basically something between, I would say, stability network and the device, you have put something. So you have to recheck your stability again. Okay. We know after this, if you put anything, it won't harm the stability of our device. But if you are putting anything in between the stability network and the device, then you have to recheck the stability, whether it is unconditionally stable or not. Whether it is still unconditionally stable or not. But if you are putting anything in between RC and the device, then you have to basically recheck. And if it is not stable, then you have to again retweak the value of R and C. Okay, so that's why I have by the final stage only I have found the R equal to 100 and C equal to 1.2. So you might get some other value in the first stage, but while designing, while you go through the steps of the design, you will be able to find the different value. Okay, so you always have to change these values, okay, as you go on a design. So you can see here the gain has become a little higher, and the fact of that fact is only is that you can see here we have basically with this transmission line that is for pad is basically making some sort of matching also. So it is basically shifting this impedance towards 50 ohm. So basically we are getting some gain enhancement also. Okay. So this is all about the device pad with the stability. Till now, if anyone has any doubt till now, so they can ask. Otherwise, we'll go ahead with the other concept. That is, now we will basically we have to put the bias network also to our device. Right now we are using the S parameter file, that is okay, but what in actual scenario we have to anyhow put VG and VD to our device, so we have to basically design that biasing network also. Okay, so before going to that, if anyone has any doubt up till now in design flow, they can ask. Yes, RC network should be meshed with the. So that for that part I'll come later. So that how to put RC network. Okay, so we will put ads for that also. So that will come in the subsequent notebook files. Okay. So I will show you how to put those pads and include it in the simulation. Before that, I will introduce the biasing. Okay, because before RC also the topology that I used to follow. I always try to put bias as close as possible to the transistors. Some papers you maybe find where people used to put RC network before the biasing network. Okay, so they used to follow this topology. Okay, so what they do is with the transistor there, they put RC very close to the basically transistor, and then here they will put biasing. Okay, and at drain the biasing will be here only. But what I found with this thing is that if some leakage is there, if current is following here, then basically it with this resistor value that if voltage starts dropping at this resistor, then this VG will vary. Okay, so that will leads to some oscillation. So in MIC circuits, because in MIC the variation can be high. So what I think is we should always put bias first, so that our VG should be fixed. VG should not vary while we are running basically the, I would say the amplifier. Because one other thing also is that if somehow sometime while running, if let's say the value of resistance become high because of some variation, or maybe because of some temperature range, then if the current should not be flow through, but in GAN the current of microampere range will always flow. So if the value of this resistor becomes high, and it starts the voltage here, let's say you have put -3 and you are supposed to have -3 only here, but with this current flow the voltage will drop, so it will vary. Okay, so it will, the -2.9 will reach, or maybe then again the resistor value will change, it will, then you will have -2.8. So VG will change, that will change the ID value, and it basically oscillates. Okay, so if it is oscillating between this value, then this ID will also oscillate, so it will lead to oscillation also. So that's why I prefer to put bias first and then RC next to it. Okay, so that's why I will first design the biasing network first, and then I will tell you how to put RC also with the pads. Okay, so how to put pads, and then we in actual, when after fabricating we will solder RC like this. Okay, so this is there. So you see, if any other question is there. Biasing should also contain some register component and connect to device. Yes, so for that I'll come next. Okay, so for that I'll just come next. I have seen that in LNA before inductor and after inductor. Okay, thank you. Yes. Okay. Okay, so I all the questions are answered now. So I think more questions are here. So I will just introduce you to the concept of biasing first. Okay. So we will see what is basically biasing is. Okay. So how we achieve it in this domain, how we achieve that part. Okay. So I just want a new page to be added here. Okay. So here we will see basically our target is and how we are achieving it. Okay. So first of all, uh, uh, as I have already told you, so basically we have a RF coming from this side. Okay, so basically we will have some block here, and we will have some block here also. So we will have DC here. Okay, and we at the transistor level. Okay, at transistor, what we want is a DC, basically DC plus RF both. So this is nothing but our bias T. It's okay. So this is also known as bias T. Okay, so so somebody can tell me if they guys know, or even if they don't know, if they don't know the concept. So we know that we do not want this RF to lead to this DC, and we do not want this DC to lead to this RF. So what is the possible solution for block 1 and block 2? Okay, so what should we put for block 1, and what should we put in block 2? Okay, so that this RF should not lead to DC, and this DC should not lead to RF. So what should be the possible solution? What component, or what thing, or what combination of components that we can put in first block and in second block? Can somebody answer that question? Okay, so you can write that yes, in first block you can put this, in second block you can put that. Okay, so I would like to see some answers. Okay, we are getting some answer. I will read out after like 4 or 5 people if answers. Uh, so I am waiting for other people to answer the question. Okay. Okay, we are getting some new names also. This is good. That usually we used to get replies from only those 20, 30 peoples only, but today I am seeing since morning that we are getting responses from like from other new names also. So that is very encouraging for me. That yes, people are getting interest. Okay, so they are, so this shows that yes, they are basically understanding what is happening. So any other replies? Okay, so we have got so much of replies that first one is capacitor in block 1, first capacitor, second inductor in series in block 2, capacitor, inductor, IR in parallel with C, first R in parallel with C, second only R. Okay, put a simple low pass filter in series with DC line. Low pass filter in series with DC line. So this is someone new that replied, I think, for the first time. Hakeem. I think this guy is given a very good solution that we have to put basically here in DC line. We have to put a low pass filter. Okay. So basically that's okay. Capacitor, inductor, that is there. Okay. So you guys all know the solution. Capacitor and inductor, everyone, I think 10 to 15 people have replied. I think more than that. Still we are getting replies. So that is good to know that yes, you guys are understanding. But I just want to make it a point here is that how to how you are thinking that. Okay, if you already know the solution, that is different thing. But I just want to make I just want to make you guys to think in some flow. Okay, so that's how you always target any problem. Okay, here the solution of the problem you know already, maybe, or maybe some of people have think it for the first time. But how you should think, that's what is my target. Okay, I always wanted the person to understand that how you have achieved those those things. Okay, the the Newton has discovered laws of basically gravitational force he has discovered, but how he has discovered? There was some flow. Okay, some the apple falls on his head, then he thinks that why he has come to down, why it is not come, it is gone upward. So that questioning, it makes him to realize that yes, whenever we are throwing anything upward, it is eventually coming outward. Basically, it is eventually coming downward only. So there is something. So that will lead him to think that yes, there is something that is basically making this to happen. That whenever something is going upward, it is making it to come downward only. Okay, so what is happening is that someone is basically pulling that thing to the ground. So pulling means what? Basically, someone with the force, it is pulling it towards itself. So that's how it reaches to the conclusion that yes, there is some force is there. So he named it as gravitational force. So that is basically the flow. Okay, so why? First, first of all, you question why it is happening there. Then you basically support it with some of your theory content, and then you eventually leads to the result. Okay, so here also the same thing is happening. uh, uh, there might be n number of possible solution, and for the matter, I would say everyone's answer is correct. uh, if even if someone has thought of a resistor also, that is also correct. Okay, but I would say I have already told, in basically this RF path we always avoid resistor. Here the stability network RC, that is our, I would say, that is our that is there, it has been forced to us to use RC there. We have to achieve stability, but otherwise we always try to avoid in RF path, we will try to avoid resistors. Okay, but yes, apart from that, what you can see here, that you want some frequency to pass here and you want some frequency to be blocked. So basically what you want here is a high pass filter. Okay, you want a higher frequency to be passed and lower frequency to be blocked. Okay, so basically you want a high pass filter here and a low pass filter here. Basically you want DC to pass and RF to be blocked. So you want a high pass filter here. So what you have to design here as a high pass filter, sorry, a second block as a low pass filter. Okay, so that's how you should think. Okay, so you, this should be low pass filter and this should be high pass filter. Okay, so you can design high pass filter with any number of components. Okay, so you know that how to design low pass and how to design high pass filters. So you can design any number of components. You can just put one inductor here. Okay, you can put one capacitor only here, or you can go ahead with capacitor and put one inductor in short also. That will also give you a much sharper response. Or you can put multiple blocks here, or you can do the same here also. Okay, so you can put capacitor, then again inductor, then capacitor, and then and again inductor. So any number of components you get. But the basic idea is that what you want here is a low pass filter, and what you want here is the high pass filter. Okay, even if you know that we can achieve high pass low pass filter with resistors also, but as I told, we always try to avoid resistors. Okay, so we will take just the simplest case of one single component only. So we will achieve this bias T with single inductor here and single capacitor here. Because to block the DC, because to we do not want a very good high pass filter, we just want to block DC here. So this DC can be blocked by any capacitor. Okay, but we want to pass this RF also, and in this capacitor should behave as a high pass filter only. So what we want is that the cutoff frequency of by putting this capacitor should be low, at which the RF frequency we are operating. Let's say we are operating at 5 gigahertz. So the cutoff frequency by putting this capacitor should be like as low as 1 gigahertz or maybe 500 megahertz, so that we do not have any attenuation at the 5 gigahertz. Okay, and same is true for this inductor also. Okay, so we want it will be acting as a low pass filter. Okay, so what we want it is basically that it this cutoff frequency as low as possible. Okay, so we want this inductor to be as high as possible. Basically, we want it to be infinity only. Okay, so the impedance through this, that j omega l should be infinity, but we know we cannot reach infinity, so basically we have to define infinity here. So anything which is giving basically j greater than 1000 or maybe j greater than 2000 will help us. Okay, so but I told you guys that at gate, is it okay? It is okay. We can put inductor, but as we know, the GAN device, we have seen the current that is flowing at even at the quiescent point only was 340 milliampere, and when we basically increase the P in, basically when we increase the P in, our basically current will have a this is basically I quiescent point. This will be IQ, but when P in will increase, this IQ will be have this sort of swing. So then this basically a DC current will increase. Okay, so the average of this will be increased. So this can even go up to 2 ampere. So this inductor cannot handle this 2 amperes. At drain, we cannot put inductor because if we put a inductor with this much of current handling, then this will have a very high parasitics. Okay, so that will basically affect our performance. So what we want to replace this inductor with something so that it can have high power handling, and it also serves the purpose what is this inductor was serving to us. Okay, so how we can achieve that? Can somebody tell from our previous lectures how we can achieve basically here what we can put here instead of inductor? From previous lecture, we have seen some techniques so that we can replace inductor. Can somebody tell some way so that we can replace inductor here? If you can see here, just for your hit, this inductor is basically nothing but is in shunt. And as you guys know, if you have studied in your BTech, the DC and AC analysis. So for AC analysis, this inductor will be short. Okay, so when you put DC here, so this inductor is nothing but short for a AC analysis here like this. So this is basically a shunt inductor here we have. So instead of this shunt inductor, what we can put here? Any solution? Okay, it is acting as a choke. That is okay. Any solution that somebody can give, what we can put here instead of this shunt inductor here? Because this is our main RF path. This is our main RF path, and this DC line is acting as a shunt here only. And for RF analysis, this DC will be shorted. Okay, when we are doing RF analysis. Okay, so somebody is saying series capacitor. No, we cannot put a series capacitor instead of DC line because what we want is we want some DC to be fit from here also. Okay, so we cannot put a series, not transformer. Just think from the previous lecture, we have seen some technique. So do not give me other solution. Just try to remember something from the previous lecture. We have seen something so that we can implement this inductor in some other form in filter while we are studying filters. Yes, stub. Okay, so I have given so much of hint to you. So basically, what we can do here is we can put a short stub here. Okay, we have to do nothing. We have to just put a transmission line, and we can apply DC here. Okay, so for RF analysis, this DC will anyway be shorted, and this shorted transmission line will act as this inductor only. Okay, so you know this thing. The Zn of a shorted transmission line. Okay, so the Zn of this transmission line is nothing but JZ0 10 beta L. So you know that thing. Okay, so the best part of this thing is that if you take L equal to lambda by 4, that means beta L is 2 pi by lambda into lambda by 4. That is lambda cancel pi. Oh, sorry, 2 4 pi by 2. So what is the value of 10 pi by 2? So you know that J Z naught 10 pi by 2, what will be having? J infinity here. So we will be having very high impedance if we put a shorted transmission line of length lambda by 4 here. Okay, so you can see here how things how with transmission line we can not even able to replace the inductor. We are able to get a very high value of inductance, also very high value of impedance that we are able to get, and we can pass DC through it, and it will block the RF. Okay, so that's how we will change from inductor. So that's how we will able to easily eliminate the inductor, and we can use inductor at gate also and drain also, so that we do not have to use that bulky inductors that are not even able to handle the basically the current that is gonna flow through our circuits. Okay. Yes, the transmission line stuff. Yes, now you are right, Tyachni. So that is there. Okay, so I hope you guys understood that. Yes, at this end we can easily use capacitor, but at instead of inductor, we what we can use is a transmission line of length lambda by 4, at the top of which we will apply DC. And for RF analysis, this is nothing but a short. Okay, so this will act as a shorted stub here. Okay, because this is our main path of RF, and for RF path, this will act as a shorted stub of length lambda by 4, and its impedance theoretically it is coming out to be infinity. Obviously, we know when we make lambda by 4, it won't be exactly lambda by 4. It can never hit lambda by 4 exact. Okay, but yes, we can be very near to lambda by 4. So we come to that value that we have J Z naught 10 beta L. So we will try to make it as close as to lambda by 4 value only. But if it is not very close to lambda by 4, what we can do is we can make it high also. We can make Z naught very high. Okay, we can choose Z naught as high as possible. That also will increase our basically this value, the impedance here. So this will also increase. So what we will do, we will try to be as close as to lambda by 4, and we will choose Z naught to be as high as possible. Okay, so this is basically the design of a bias T, and I am telling you, there are companies who are just designing this bias T with different frequency band, with different power handlings, and they are selling it in basically in lakhs. You can search on the internet the bias T, and you can just see the cost. You will find that there are specialized bias T only with this concept, with this small concept only, but just what they are doing is they're designing it with some specific specification, that yes, we are having some specific band, or maybe with some power handling. So as the specification become more and more, the cost of bias becomes large and large. And we have bias which like only one bias which can cost up to 10 lakhs also. Okay, and you can see basically in this RF domain the value of the design. Okay, so but you can see the principal concept is nothing much. Okay, but as soon as you make it more and more reliable and more robust with the specs, it the cost becomes higher and higher, and the design is nothing but the same only. Okay, so that is basically the thing. Okay, so you just don't think you this bias is nothing, is very small thing. I'm telling you, people are doing just startup using this bias only, using filter designs only, using coupler design only. So there are that much of requirement of these components, and you are basically designing all those things in this one single workshop only. Okay, so you have designed filter. Okay, so you have now today you have designed bias T. You will design power amplifier also. If time permits, I will teach you combiner also. Tomorrow you will. Tomorrow I think I will teach combiner and LNA both. So you can see you have learned so much of designs in a single workshop only. Okay, at least not learned. I would say to totality, but yes, you must have got some idea that yes, how the things works in RF, how you have to go for a design, and what are the importance. Okay, so this is not so. I would say this is not. These are not so easy tasks, but yes, the way I am telling you, you will find that yes, it is achievable. It is not. It is not that difficult too. Okay. So I think that's all for this session. In the next section, we will design it, the principle that we have learned now. Then we will go for the design of the bias T, that how we will design it, how we will include it in our simulation, and again that the bias pads of the RC also. And after that, we will see how we will match. Okay, so we will see two ways of matching, and then our power amplifier design is ready, and we will see the final layout also. Okay, so that's all for this session. We will again meet at 12:15. So I will hand over to Firoza ma'am if she wants to basically share anything regarding, or if she wants to announce anything.
Yeah, thank you, sir. So we are closing for the first half of day 8 session. Dear participant, again the announcement is regarding the quiz. The quiz will be conducted today from 2:30 p.m. to 2:50 p.m. This will be quiz number 4, and tomorrow we will be having quiz number 5. The timing for quiz number 5 will be from 2:10 to 2:30. In between the lunch break, we will be doing the quiz because tomorrow the session will be ending at 4 o'clock. So I request you all to please check the schedule. It is already been uploaded in your Drive link. So with this, we will be closing the session. Now there will be a testing, like 5 minutes of testing with one of the experts. So please ignore the testing part. It is only for the next day session. So we will be testing. It is not a part of your course curriculum. So thank you, Ashish sir, for this session, and thank you, participant. Please get connected with us by 12:15 again. Thank you. Hello, good afternoon, sir.
Yeah, good afternoon. Can you hear me?
Yes, sir. Your audio as well as video is clear, sir. May I
Okay.
request Pubali, can you please? Okay. Sir, we have given you the presenter right, sir, right now. If you can see, there is a circle.
Sorry.
So you can just try. So we have given you the
Uh,
presenter right. So now you can
okay,
share the
okay,
content, sir.
okay. Just a minute. Okay.
Yes, sir.
Uh, so I there should be something, some button for presentation, right?
Yes, sir. At the bottom, sir, you can see there are three icons. First is for the speaker, second is for the start my video, and the third is share content, sir. At the bottom, sir, there are three
Share
icons.
content. Yeah. Share content is there. Okay, okay. So from the share content, I can go to screen or what? Should I share my screen?
So you may either share your screen or you may open your presentation slides beforehand. Then you'll get
Okay,
the option of presentation, PowerPoint presentation also when you click on share content. So you
okay,
can
okay,
opt
okay.
for any of the two options.
Okay, let me try.
Yes, sir.
This is a different presentation I am trying to share with you. So, share content. Okay. Can you see my screen?
No, sir.
Okay. See.
Yes, sir. Now it's coming. Yeah.
Yeah. Can you see the presentation, right?
Yes, sir.
Okay. So I am changing the slides. So just see whether it is
Yes,
changing
sir. The
properly.
slides are changing. Yes, sir.
Okay. Okay. So, okay. So actually, I have gone to share my screen. Then I have opened this PPT. So you can see both of my video as well as my PPT, right?
Yes, sir. Your video is also clear and the presentation slides is also clear, sir. It's visible.
Okay, okay. So I think it should work properly.
Yes, sir.
Okay.
Yeah.
So, so whatever is there in my screen, you can see it, right?
Yes, sir. Now you're
Okay.
yes, sir.
My Explorer, Windows Explorer. I mean, if I want to show some simulation, that also you can see. Okay, then it should be okay.
And so we are having the Q&A section also. So
Yes.
where the
One.
participants are putting their questions, sir.
Yes. So you require five multiple choice questions, right?
No, sir, not for that. So like during the session, if the participants are having any sort of queries, so
Mm-hmm.
they're putting those queries in the Q&A section, sir.
Q&A.
Their query. Yes, sir. So it's in the right hand side button, also you're sharing your screen. So if you take the cursor at the top of your screen, you will see a
Mm-hmm.
panel coming down.
A panel. Yes, a panel is there.
Yes, sir. So there you will get one option is Q&A
Q&A.
section. So beside the chat box.
Just Actually, right now I can see a small window on the right side where I can see EG. Some EG is there, and then the next page. Okay, so it is showing. So actually, this WebEx is right now showing in a minimized window. You
Okay,
can
so like yeah, so it's in the top right hand side of the screen. So you'll get like several buttons are there. You can choose whether like what type of view you want to have.
okay,
The three options are there. You can select any one of
okay,
them.
okay, 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 okay. So these three options are there. One is telling about show active speaker video view. Then it is showing about this grid view. Then it has uh, active speaker and thumbnail video view. So you are talking about these three options.
Yes, sir. So you can select any of these in whichever you are comfortable.
Okay, okay. But I didn't get this Q&A.
Q&A section, so like whenever you take whenever you're presenting your screen, and if you take your cursor at the top of the screen, a panel comes down, so where several buttons like participant details, chat box, mute, video options, those things came up.
Okay,
So there's a one of the option button you can find as Q&A section.
okay. Yeah,
So now
now
since you have stopped sharing, now that Q&A section will be on the like right hand side button, like bottom of the screen.
okay. Let's try once again. Hmm, share screen. Yes, the Q&A section is there on the right side of the screen.
Yes, sir. Yes, sir. Yes, sir.
So now, can I see both the in one go?
Yes, sir. That can also be done.
Okay. So
So
let's.
for that, sir, first you have to share your screen.
Okay.
So you can stop sharing the slide. The slide will be up.
Okay. Okay. So I have stopped sharing. Now, if I want to disconnect, then
So you at the bottom
just
there is a cross. Yeah.
yes, yes, yes. Okay. Leave event. Okay.
Yes.
Okay. Okay.
Thanks a
So
lot, sir, for joining us.
okay. Thank you for helping me out. So I'm leaving. Okay.
Yeah. Thank you, sir.
Sure, sir.
Okay. So
Thank you, sir.
okay. See you on Friday. Okay. Thank you.
Yeah, thank you, sir. Sure. Sir. So good afternoon, participants. Thank you for staying connected with us. We had a small testing session. So now we will be starting our session for day 8, second session. So please, Anshul, you can continue. And regarding, sorry, Ashish sir, you may
Ashish.
continue. And yeah, Ashish sir.
Yes.
And regarding the quiz, we already made the announcement. Today we are having the quiz from 2:30 to 2:50. So please get connected to, please click the Google link at 2:30 and please submit the response before 2:50. So sir, please continue, sir. Thank you.
Okay. Thank you. Uh, so let's start with our second session. So in previous session, we have seen that we have to basically design a biasing network. We have seen a scheme of that. Now we will include that. Okay, so there are some questions here. Stuff which does not allow RF to DC. Okay, so basically the stub here is the shunt stub. So what is that stub is doing is that the RF which is going, it does not allow anything. The RF should not leak here. Okay, so if it is leaking, it should be in the permissible values only, and DC can always pass. Okay, so this is just nothing. The transmission line is nothing but just a metal, and if you put any voltage on that, it will pass through it, and you will get DC out here. Okay, so that is basically our design of a bias T. So at the end, I told you guys that this was the basically the, I would say, the input impedance of a shorted transmission line. So we want this Z0 to also to be high. And but from our past lectures, we know that if a Z0 is high, then W will decrease. Okay, so if you take a very high value of Z0, the W will decrease. But at gate side, it is okay. So we can have a thinner line at gate side. So because at gate we do not have current flowing through gate of a device, but at the drain we have a high requirement as high as 2 ampere. Okay, so we cannot make Z0 very high at drain side. Okay, so that is limitation because of current handling. So at that we have to make that width so that it is able to handle this much power, this much current. So generally it is known that the 700 milliampere per I think per I guess 500 for 500 micron the current rating is like this 700 milliampere. So for this design we have chosen width of around 100 micron basically. So 1.1 mm width we have chosen as per the current rating. So that current rating is given by the substrate. In the substrate, it is written that the metal line, how much current it can handle per micron. So according to that, you have to keep some safer margin also. So according to that, you can choose any width so that it will be able to handle your maximum current. Okay. So we have chosen 1100 micron. So now, first going ahead, so we will take this question first. So if our RF signal has high bandwidth, 4 to 6 gigahertz, shortest stub won't act as a good inductor for whole frequency range, and hence some frequency component may go to DC supply and may damage it. How to avoid this? So this is very good, I would say, observation. I was just coming to that part only, but as you have asked it now, so but what is basically done is this is we have used just a shorted stub. So what we do in actual, what we do is we use some capacitors also here. Okay, so some series of capacitors we use. Sorry, that will be in parallel. Okay, so these capacitors will make sure that the other frequencies which is not able to be like some components which are going through this will get shorted through these capacitors. Okay, so in bias T we just do not put the transmission line here only, we put the capacitors also. So but while designing the amplifier, these capacitors we do not put in our simulation because these are just to short those frequencies. So these capacitors, if you put after this transmission line, it won't give you that much effect. So but while actually fabricating it, okay, so you put this capacitor bank. So this capacitor bank serves two purpose. Okay, this solves two purpose. First, the one that is this Soham has asked that whether the other, if your RF signal has higher bandwidth, so it might possible that for some frequency component it may leak out because this shorted stub will not stop all the frequencies. Okay, so it will be stopping only the center frequency. So that's why we have kept Z0 high. Even the length is not lambda by 4. If it is be a little below for other frequencies, this not high will stop those frequencies. Okay, so that's how we manage. But still, if there are some frequencies for which it is leaking, then it can be shorted through these capacitors. Okay, so this capacitor will act as a low pass filter. In shunt, it will act as a low pass filter. So they will also short this basically I would say the all that frequency. Okay, so that's how basically what we are doing here is nothing but just we are adding components. Okay, so that the lowermost cutoff frequency will be as low as possible. Okay, and the other purpose that it serves is that I already told that in DC also we have ripples. Okay, we never able to get a pure DC from real DC source. Okay, so it will always have ripples because it what is doing is it is converting a AC signal to DC signal, which will be form of like this. So this will have some frequency components which can range from even kilohertz to even up to megahertz frequency components it will have. So that can also pass through this thing, and it may lead to instability of the device. So that is also to be filtered out, and that these things will be filtered out this filter bank also. So you have to make sure that you have to put as high capacitor as possible. So we for basically to remove out this frequency components, we put one capacitor of 1 microfarad and even 220 microfarads capacitor also to just to make sure that this ripples won't pass through. And even if it is pass through, then for that we have already we have installed a RST stability network so that our device won't go in an unstable region. So I hope this answers your question, Soham. Uh, I would say this was a very nice observation that you have made. But while designing, these capacitors were just put in your fabricated circuit. In design, I have not put this capacitor, but later on you can try putting these capacitors also, and you will see that this won't affect much the simulation results. Okay, but you can always put while designing, you can always put this capacitors. And what we used to do is to basically we use series not series, basically in parallel many capacitors. Okay, so this capacitor bank is generally known as filter bank. Okay, so it includes values from like 1 perf, then 10 perf. So basically we take a value in each tens. Okay, so 1 perf, 10 perf, then 100 perf, and then in 1000 perf range. Okay, so any values in these ranges we can take, and we can even go ahead and we can take 10,000 perf also. So we need to put all this capacitor in parallel because as you know, as the value of capacitor increases, its RF value will decrease. So in practical, in theoretical scenario, only this capacitor should work, but SRF of this capacitor is not high. So that's why we have to put filter banks of other capacitors, because the cutoff frequency through this capacitor is a little high, and through this is smaller. Okay, but with this all bank we will able to achieve a good response. Okay, so this is basically known as a filter bank. So we have put this all in parallel because with the higher values, the SRF value of capacitor will be very low. So for higher frequencies, to block higher frequencies, we have put a lower value of capacitor whose RF value will lie in those ranges. Okay, so that's why we have taken our capacitor of all range values. So it is basically called filter bank. It always used with the DC supply before giving a DC to your RF circuit. Okay, so it will put, you always put those capacitors. So basically your DC supply come here. Okay, and there will be filter banks. All the filters will there, and then this will go to your transmission line. Okay, so this will reaches to your transmission line. So from here your RF analysis will start. Okay, so for us this is all shorted, so we will consider it as shorted only. So this part will be your DC part of your circuit. Okay, and below this is all what is the RF part of your circuit. Okay, so coming to the design, we have basically included in our design for a package the pads. Okay, so the pads we have already put. Now we have to put a basically shorted stub here and a shorted stub here. Okay, so that is what we require, and a DC block. Okay, so before going to the gate, first we design a drain network in which we need a shortage stub here. Then we need a pad. Basically, why we need a pad? Because we have to connect a capacitor here. Okay, so what we require to put here is a capacitor. That will be this block. This is a capacitor, and then again a pad here. So that this capacitor will be put in on these two pads, and this will be our transmission line. That shorted transmission line will be there, and this will act as a bias T. Okay, so DC will come from here, and RF will go, because drain. So RF will go from here. So here we will get RF. Here will be have DC, and here we will have DC plus RF. Okay, so this network, that is what we have to make. So up to DC pad. Sorry. I would say this uh, the pad of the device that we have already made. Okay, so we have already designed that pads with this M1 length. Okay, so L1 we have designed. Now for the, I would say, the bias pads. Okay, so for biasing, the to calculate lambda by 4 with this, I would say, substrate, you will get the values for a shorted stuff. Like it will become a little less, but after tuning you will reach. Okay, so you can just calculate those values, and you will find that the value of the length is coming around like this value only. And when you put it here, you want this stub to be of length this much. Okay, so this is L drain here. Okay, and after that we have put a 0.25 micron pad, because the SMD component that we are using here will be having a pad of around like 0.2 mm. Okay, so 0.2 mm on both the sides. Okay, so basically I have put it 0.25 so that it won't touch this drain line. So the capacitor will come here, and the basically the here below it is the length of like between the pads, the length here is 1200 micron. So we will leave the gap of 1200 micron, and then we put another pad here, and which we have put as a 0.5 mm. Okay, so basically, so you can see here that is the length 4. This is L4. This is L3 basically, and then L drain. Okay, so then how we have connected it to the device? So somebody has asked a question that what's the use of putting capacitance value low? So where which capacitance you are asking? Which value you are asking as a low value? So, which a stability capacitance, biasing capacitance, or this blocking capacitance? Which capacitance you are asking? Marley Solomon, I'm asking you if you can tell. Okay, so if you can write. Meanwhile, I can continue with the design. Okay, so you can see here we have designed L3, L4, L drain, and after that we have just we have did nothing great. Just basically created device 1. Okay, so this device will be having with the device pad. This is the drain pad. After that we have a shorted stub L drain. After that we have that 0.25 micron line, and 0.25 mm line. Then we have a blocking capacitor. So the primary purpose of blocking capacitor, you all know, will be to block the RF to be leaked to the sorry, to block DC to lead to the RF source. Okay, and then we have a line 4. Okay, so this line 4 is basically this 0.5 mm. So this has now become our device 1, and after that we have put the same stability network to that. And when we run this code, okay, so when you can run at your end and see whether you are able to run or no error is coming. It should not give any error. Uh, so when we run this thing, you can see here the response changed a lot, and we have basically achieved some gain also at our frequency range. Okay, so because this line what we have designed is for 5 gigahertz, so we have achieved some sort of matching also at S22, and we have also achieved some gain also. So what is the biasing network here is doing is it is also providing. So as you can see here, S11 is also shift a little, but S22 is also basically become around here. Okay, so it is coming closer to our basically the center point one here. And what is basically happening here is this drain line and this blocking capacitor, basically this bias T also is acting as a impedance matching. Okay, so while designing this L drain and C block, you can always tune the value of drain length. Okay, so you have put some values, you by calculation, by theory, you have calculated some values, you have put that, but after that you can always tune those values and basically optimize the response here. Okay, so I have just optimized so that so at 5 gigahertz I will get some sort of a good gain, and a little match also at S22. Okay, so it basically ease out our impedance matching requirements at a later stage. Okay, so that's how we do it. Okay, so just to show you the I have one I have the layout also. Okay, so you can see here. So this is basically what we have designed till now at the drain side. Okay, so this is basically what we have designed. This is you can see here. This is the device pad that we have made. Okay, so this is the device pad at the drain. After that, we have a shorted stub here. Okay, so I have just bent it down like this so that so that it won't go ahead in above and it increases our y size. So we have just bent it a little here. After that, here you can put a pad here like that. Okay, a pad here. Sorry, you can always put a pad here. So you can put a pad like this here, and a ground pad here like this. So this will be ground pad. So this is a ground, and you can put your capacitors here like this. Okay, and you can put your DC supply here, the positive supply and negative supply here, and that's how you make a ground. Okay, so just make sure that the this pad should not be as big that I am showing. It should be like small pad only. It should not be, otherwise it will start acting as a stub. Okay, so what we want is, so we want the things to be basically grounded at as close as possible. So what we will make is this pad to be small, but the ground pad we can make a big. Okay, so for strength we can make a good big ground pads, and these are the via holes so that we can connect the top metal. Okay, so these are the vias. So through this we connect this top metal to the bottom metal, and which will make this pad also ground. Okay. Okay, so here you can put capacitors like this. Those 5 capacitors that I was telling, you can start the capacitors values just very much next to it, and here, and then you can put your DC supply here. Okay, so then after filtering, you will get here, and for RF analysis, this will act as a short. Okay, so that's how the things are made, and after that, this will be that 0.25 pad, and then in a gap of 1200 micron space, and then we have a 0.5 micron pad. Okay, so that's how the I would say this layout has been made at the drain side. Okay, and we have seen that yes, this line of drain and the capacitors value can be tuned, and we can have a way see the value of S22 and S21 so that it becomes a good match, because this biasing network also is acting as a impedance matching network only. Okay, so basically blocking capacitor and the shunted stuff is basically helping us to achieve matching also. Okay, So there are basically some primary purpose of both the things. Okay, so stability network, the primary purpose is to provide stability for DC blocking capacitor. Primary purpose is to stop RF, or sorry, to stop DC to leak to RF source. Or and for the scientist stuff, what we want is to stop RF to leak to the DC source. But as a basically it is also providing a sort of impedance match also. Okay, so you have to basically look at the S11 and S22 also while designing this thing. Okay, you cannot just put anything here. Otherwise, it might happen that it rather making it better towards the impedance match, it can take you very far away from the from 50 ohm. Okay, so that will basically make your design narrower, and it might possible that you won't be able to achieve the specs also, or you won't be able to achieve the matching at the end. Okay, so you have to take into account all those factors also while designing. Okay, so you have to basically fulfill the primary purpose, but you should also see to these factors also, the S11, S22 and S21, while designing all these things. Okay, so you have seen that yes, we have put capacitors to have to basically to be soldered on this layout. So that's how we make layout. And as of now, you have seen that we have considered each and every transmission line till now. Okay, so we are not removing any transmission line that can be a part of a RF path. Okay, so we cannot avoid any transmission line that can be come in a path of a RF path basically. Okay, so that's how we basically we include each and every transmission line for our design. Okay, so that's how we are going here. Okay, so the width here also. Okay, so this width I have chosen same as this width, because otherwise if I take it a little narrower, okay, that also we can do, but that will anyway include some step discontinuities. Okay, so that will also affect our response. So that what we do not want here. So that to just to avoid that, I have used this. But so you can basically tune the length of this pad also. Okay, so you can take in tuning the length of this pad and width of this pad also, and see whether with by changing this width and length of this pad, can we somehow make your response better at this stage itself only. Okay, so the primary purpose of this pad is to put a capacitor, but if by increasing that pad, if we are able to achieve a good response, then we can always increase this pad itself here. But if by decreasing we are getting better performance, then we have to put some minimum value only. Okay, so that minimum value is required for putting capacitor. So that minimum you cannot avoid. Okay, so that's how you have to think while designing the amplifiers. Okay, so now what we have completed is that we have completed the output side bias network with the drain pad along with the bias network, and we have also have the stability network also at the input. Okay, so with that, we have some sort of response here. We have achieved some response of a power amplifier. It has started looking like a power amplifier, or I would rather say amplifier, which have some gain, because initially it has nothing gain. So you can see as 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 you have started matching your transistors towards the 50 ohm, it has started giving you the gain, and also the return loss are becoming better and better. Okay, so that's how you basically go about designing a power amplifier, or rather amplifier, you can say. Okay, so after completing this, what's the next step is to basically design the same biasing network for your gate side also. Okay, so now our task is to basically design some I would say the same thing for the gate side also. So what is basically done here is we have designed the output side thing. Okay, so I will not draw that part, but yes, we have a package here. Okay, so this is our package. So this is our pin. So we have put it on a pad. So now we have a pad. Now what we require here is to put a basically shorted stub here. Okay, so at gate there the requirement of current is nothing. So we will take Z note as high as possible, and for that Z note, we have taken the width of this transmission line as 0.2 mm. Why we have restricted to 0.2 mm? Because the printing facility from which we have printed the circuit, the requirement is that he cannot print the line with the width less than 0.2 mm. Okay, so that's why we have restricted ourselves to this 0.2 mm only, because otherwise the if he prints, the transmission line will come like this. So this is not desirable. Okay, so that's why he says that I can print safely the 0.2 mm line. So I have chosen this line to be 0.2 mm. For that, that not comes around like I think 100 or 100 or more than 100 ohms. Okay, so that you can check at your end using line calculator. And then we have designed the length here also. So that is nothing but the same. I think the same value comes for the gate length also, the 16 mm only. Again, this is a shorted stub. Okay, so this is to provide bias. After that, what we put is now DC block we can shift apart from the RC. Okay, so because now we have a DC here directly, so now first we will put our stability network after this. Okay, and then we will put blocking network. Okay, so now this is what we have to design. So for that, what we require is we have to put a pad here first. Okay, so we need a pad here. We need a pad here also. So that will include this RC and this C one side also, and then one pad here. Okay, so that is what we need to include in our design now. Okay, so that is basically we have to do. So that's how. So we will do it like this. So we have a package here. Okay, so we have a gate pad, then we have a drain transmission line. So I am showing it with a very thin line. So it is basically sorted. After that, we will have a pad. Okay, so that the R and C both can come on that. So we will have a wider path. So what we have done is we have taken this path, this pad size only. On this, both RC can come. Then a gap is there. After that, we have one pad, and we have a small pad here for basically the capacitor. So this will include the capacitor here, and after that, we will have the final pad here. So that's how it will come. So this will be C, this is R, this is C, and these are the three pads, and this is gate line. So so you in the code you can see uh, uh, here the basically this L5. So this will be your L5. So this will be your L5. This is L6. This will be your L7, and this will be your L8. Okay, so this is L5, L6, L7, L8, and the width of all of this line is defined as the length of width of L5. This L5 width is same as this size, and this L6 is also same because we have to put RC. But then L7 and L8 is we have kept it as 50 ohm. Okay, so wherever the pad side is not required, we always try to put 50 ohm lines. So that will always help. Okay, you can put any other line always. Anyway, I have told you that you can put all this widths and line in tuning, and you can see whether while changing these lines can change your response a little bit, or whether it is improving it or whether it is degrading it. If it is degrading, then yes, you put those transmission line as minimum as possible. And if it is improving it, you just see, but by increasing how much it improves your response. And if you find it that yes, by putting it there I am getting better response, then you can always put those transmission lines. That helps you to get matching with the easier matching networks. Otherwise matching will become very difficult. Okay, so we are basically, by putting this transmission line, you can now, I think you are now in a position to understand it better, that yes, what we are basically doing is that yes, we are creating the matching only. Okay, so with this, these are basically we are putting for a biasing and stability network, but these are also enhancing our matching. Okay, so these are basically making our device more matched towards 50 ohms. So while designing this stability and I would say biasing networks, you should always you should not forget about the impedance of the devices also. Okay, so you should always look at at those responses, so that whatever line or capacitor or inductor or resistor or anything that you have put, it should not take your impedance very far away from the 50 ohm. You should always try to put such values, such stubs, such pads, so that you are basically moving towards 50 ohm only. Okay, so that will help you to basically 250 ohm at your desired frequency. Okay, so that is what is required here. Okay, I would say this some questions are there that buffer.s2p file is not available. This buffer for I have just put it to basically check something. Delete this line, whichever line includes this buffer.s2p. Okay, so you can just remove those lines. Okay, so then you will be able to run your code error free. Okay, so this buffer.s2p, I think shared with you guys the older version of this code only. Okay, so this, as you can see in my code here, we have buffer 4 line, this line. You can just delete it from your code. Okay, so just delete this thing, and here also you just delete this buffer 4 here, and you can just write here device stability only. Okay, or for that matter, you can just delete this line. Okay, so you just delete any line that contains buffer 4. Okay, so it is nothing but buffer 4 was a measured result of this network. Okay, so so I'll just come to that. What was buffer 4? You can just run without buffer 4. You can run this code, and you can see here the basically our response is getting better and better, and we have already been reached to some level of 10 dB gain. Okay, so initially it was 1, and with a good design of stability and the biasing network, we have increased the gain, because basically we have matched the device. Okay, so after matching, we are now very much confident that we are able to achieve a 10 dB of gain, and we will able to achieve the impedance match also. Okay, so in just to show you the device, that how I have designed it. Okay, so you can see here, this was the device, the bare device. This was the same as the drain part, which we have done in the last session, or in the last notebook. So in this, we have just added, was the pad. This is shorted the gate transmission, shunt gate, so that we can have a bias. And this is the pad after that. After that, we have put the stability network in parallel. And after that stability network, what we have put, this is the pad that contains the second area of the RC network. After that, that small line that will have the CG block, and after that, this is the eighth line. Okay, so in that diagram that I have drawn, so this is how that I have created, and after that the response looks like this. Okay, so I can show you how it looks. Basically, this is the input side. Okay, so that's how we have created the input side. So here this a pad of device will come. After that, we have a shunt shorted stub here. Okay, so I have shown you how you will make a pad here. Okay, so I've just shown you a simple path. So you can just extend it here and put capacitors in parallel here, and then put a DC supply. Okay, and here the RC will come here. Okay, so here your stability network RC will come. This will come here, and your blocking capacitor will come here. So that will be SMD component. So it will be like this. this resistor will be like this, and this capacitor will be like this. So, okay, so that's how you make it. Okay, so one more thing is that at the gate, the thing I have told you that TC is not pure; it have a ripples there. So what people usually do also in the gate, not at the drain, because at drain we cannot put resistors. So they put a resistor here also. Okay, so one resistor they also put here, like this they put, so that these frequencies will face some attenuation here. Okay, so the level of this will become very small, so that it won't come as a low frequency oscillation. So people usually puts one resistor here also. Okay, so that resistor will basically degrades the low frequency oscillation that is coming from your DC supply. Okay, so you can see some of the designs in which they have put resistor here, or even for that matter, some people put resistor here only. Okay, so they put resistor here, and after that they will put this shorted stuff. Okay, so that will basically same way it will act. Okay, so you can implement this thing in your design at your end, and you see what changes it will make, and accordingly then you can change your values and retune your circuit. Okay, after introducing this resistor. Okay, so basically this is what we have designed. Okay, so in between we will have right now I am showing it with like the distance is very high, but the whatever the distance is required to put basically the device, that distance we will keep in between these two layouts, and so that our basically packaged device will come in between like this. So this pad will be like here only. Okay, so this pad will be here only. So this distance will not be that much high. I have just shown you this. This is our the input side, and this is our output side. Okay, so buffer 4 is nothing but what I have done is after designing this, I have printed this in our lab, and I have tested it with this device, and I have seen it. Okay, so when I did that, I have just checked that whether it is matching with our whatever we have designed till now, whether the response is matching or not. So that was matching at that time. Okay, so initially the response that you were seeing, like this, the buffer 4 response that you were seeing, I think I can show you guys, but I just left. I think I have deleted that file too. So what was the response was that the response was coming like this. Okay, so if you have not run, you can again download the file and you can see the response there. It was coming like this. So you can see the measured response is basically exactly matching the our designed network. Okay, so that is basically, yes, we are basically going in the right direction, and whatever we are designing, we are eventually get the result after fabricating. Okay, so what we have now is basically what we have designed is we have a network here. So this is basically now our new transistor, which has a biasing here. Okay, will have some biasing here also. So this is basically VGDC, VG, and this is basically VD. Okay, so I will just delete this DC here. Okay, so what we have here is VG, VD here, and we have some biasing here and transistor with the stability. So what we have here is we just have to match it to some ZS and ZL. Okay, so what we have to do it, we have to just match it to ZS and ZL, and our amplifier is ready at with the given specification. We might have to retune some after matching it. It might possible that we are not able to meeting the specs. Then we have to again come back to this transistor inside design, and we have to tweak the little values of bias, capacitors, RC, all those. Maybe we have to change this bias value also. So all those tuning that you have to do. Okay, so I'm just telling at each and every point of time that how you have to basically tune and what all factors while designing anything, what all factors you have to take into account while designing your amplifier. Because I have designed it for you guys, it does not mean that you can design it in one day only. Okay, if you are starting it afresh with a new device, so it will take a 1 month at least. So if you are starting it for the first time, so with tunings and all, one day you will feel that yes, you are able to design it. The other day you will include some other factor and you will say your responses will degrade a much. Okay, then again you go back to your first step and see what I can do here, so that the factor that I have included the other day, I can compensate for that. Okay, so that's how the iteration goes. And like it will take around like maybe not 1 month. If then maybe if you are working very hard day and night, then you can it can take up to 10 days also. Okay, so that depends. It might possible also that you can hit the target in one go only, but it usually won't happen. Okay, so with experience, yes, you know this can affect my response so much, or it might possible that on that device you have already worked earlier, so that will help you to have a better experience, that what we have to put, what we have not to put. So that's all you have to basically do while designing. Okay, so this is basically we have designed a stability network with bias network also, and a transistor. So that's all that we have designed till now. So if you have any question in this, you can ask me now. Otherwise, we will. If anyone has any question regarding this design till now, and I'm making sure that if you print this layout, okay, the way I have, you can make this layout in any software. Any if you can have AutoCAD, can make it in that, or any device layout design. Just make the layout as I have discussed here, as per your components. Whichever component you have, you can change the pad size and the gap between those pads, and then what you can have is you can print that and just put the device, and you can measure the S parameter using VNA. So somebody is asking that how to test this circuits. Okay, so after designing, basically what you will do, there will be a PCB. So what at the RF, so at both the ends you have the pad. So at those pad you will connect a usually we connect a SMA connector. Okay, so this SMA connector is connected, and using this basically this SMA connector will be then connected to the cables of VNA. Okay, so there is a vector network analyzer is there. So using that vector network analyzer, what is done is we can easily make, and you will basically provide VG and VD also to your device, and then you can measure the S parameter using this VNA. It will give you the S2P file, and then you can import that to this uh, to this tool only, and then you can basically see that buffer 4 file that you are seen here. That buffer 4 file is nothing but the measured S2P file from VNA only, and then you can match whether it is matching your design circuit or not. Okay, so then if it is not matching, then you can find some possible uh, things. Okay, so in buffer 4, what I have done is it was not exactly the S2P file that we have got from VNA. In buffer 4, what I have done is I have de-embedded the connectors. Okay, because up till now we have not included the SMA connectors file here. Okay, so I have de-embedded that the connector that can be done at VNA level only. Okay, so you can, it has some de-embedding routine written in the VNA, which if you put that yes, there are SMA connectors at the port, so you can easily de-embed those SMA connectors, and you will get the basically S parameter up to the, let's say this is your PCB, and this was your SMA connectors here. So initially VNA will measure S parameter at this reference plane, but after de-embedding it will shift your S parameter up to this level. Okay, so these connectors will be de-embedded from your network, and you will get the response of this PCB only, which is basically what you have designed here, and you can match whether the results are matching or not. It will not match exactly, okay. You will have some variations, but those variations are acceptable. It should not be like that. Your S21 in here is like this, and after printing, you are getting S21 like this only. Okay, so it should not come. It might possible that it shifts up in a frequency a little. It might be because the components that you are using, it have some parasitics effect. So those parasitic effects can shift your frequency response. Okay. So how to avoid that? What you can do is whatever components you have. Okay. So what components that I have used are very I of high performance at this frequency. So those have very little parasitic effects, but they are very costly also. So they are basically give performance as ideal as possible at this frequency. But what components you might have will not work exactly as a ideal capacitor. It will have some parasitics. So what you can have is that all the capacitors and inductors that you are using, there might be some S2P files available on internet or maybe in the data sheet. Okay, so whatever capacitor value you are using, you can take those S2P file, and instead of this capacitor, you can use those S2P file. That will be as good as using it as a model. Okay, the model of capacitor, and you can see that response will shift. Okay, will shift that, and then you can retune your circuit for those models. Okay, then after printing, your circuit should match with the fabricated results. Basically, your design result should match with the fabricated. So basically, I'm telling you the possible variation that can come if you want to fabricate and test it. So these are the basically possible variation that can come after fabrications. So all this factor you have to include in your design. Or you can use a better components. Okay, but always, if you want a better results or better components or better performance, you always have to pay money. Okay, so if you can afford that money, you can always use that. If you cannot afford that money, you can include those effects in your design. And obviously, with the parasitic effect, it will obviously degrade your design. Okay, so but that might possible that it that degradation is that much that you cannot even recover your response. Okay, but whatever is there, you have to manage with that only. So it you can say that yes, with these components and with this substrate and with all this thing, we cannot achieve the given specification. If you want me to achieve the specification, I want this much thing. Or okay, so that's how the things work in a design area. Okay, so you can one cannot say that you give me the specification that is giving. So sometimes basically in DRDO what we face is this thing only, that sometimes there are something from the USA or somewhere, there are some part the people are using, but in DRDO we do not have the access to those components and facilities. So we basically do not achieve those specifications, but yes, we can achieve some specifications so that our system can work. So obviously, there are some, I would say, a lag between what we can have in a world market and what we can have here in Indian market. But obviously, we can always find some other solution, other topologies, so that we can compete and we can be in line, or we can be in the race of the world. Okay, so I would say, as a as a matter of fact, right now DRDO is doing good in the field of basically RF design. So we have many state of the art radars with the DRDO. So basically, if you have heard of Mission Shakti also, so it is capable of basically destroying a satellite that is moving very far in the space. So you can read about the Mission Shakti on the internet. Many information is available. So basically in that also, what is that is a guided missile. Okay, so what it's doing is it is basically sending some signal so that it will get reflected from space and it will found its target. So once the target is found, it is locked into the missile, and it will basically hit that target. Even if the target will change the path, then also uh, uh, it will find its target and hit it. Okay, so all this, how to find it, and all this will have some sort of wireless communication only, and all those communication requires TR module, and those TR modules requires this PA, LNA switch and all everything. Okay, so this is basically has huge application in defense also. And basically right now we are focusing on 5G only, but I am just giving you a broader picture that after this course, this design concept that you have learned, it is not just that it is only restricted to 5G only. You can, if you are going for a radar design also, so for that also the TR module that is required. Only thing is that in TR module of a radar, the linearity is not an issue. So you can have PA with any number of TB of compression, but the only thing that is required is a power. You require as much as high power, and what you require is you require a high efficiency also. So you know that if you are not worried about linearity, you will have a high efficiency. So that things work. Okay, so PA with for a radar application will have a different topology, but for communication it will have different requirements. Okay, so that is basically about the PA design. Okay, so there is some question: how can we read S2P file without this tool as what is written inside it? You can simply open it with a notepad. Okay, so I can just show you. Uh, this is basically device SPRM file. When you click it, it will ask how to open it. You just open it with a notepad. Okay, simple notepad, you can open it, and if you open the notepad, you will see this sort of thing, that it is created at what time. Okay, so this sort of thing you will find. After that, you can see here this line. Okay, so this line shows the frequency point, the unit of those frequency point, and basically in which format your S11, S22 are there. Okay, so we in this S2P file, it is in the form of dB, and the reference impedance that is chosen is 50 ohm. Okay, so that's how it is written. And after that, you can see here we have frequency dB S11 angle S11, dB S2 angle S12, and for each frequency point you have all the values for each every frequency you have S11, S12, S21, S22, dB and angle of all the four components, and it will be from 1 to 6. Okay, so that's how S2P look like. Okay, so you can read it through notepad. Okay, I hope Gaurav, it is clear to you that how we can read the S2P file. So you can read it through MATLAB also. If you have a license of a MATLAB, so you can read it in MATLAB also. You can basically copy paste this notepad from notepad to a Excel, and then in Excel also you can plot in dBs. Okay, so obviously you cannot plot Smith chart in a Excel file, but you can always plot dB plot of S11, S21, S22 in Excel file. Okay. Okay, so coming to basically our the main thing, that is the matching. Okay, so in this example that we are doing right now, what we will do is we will do the conjugate match only. Okay, but in actual, after designing this stability with the biasing network, if you have a paid software, what you can do, you can perform a load pull there. Okay, so there will be a template. What it will do is it will provide all the impedances at the output and see for which it is getting the highest power. And for that impedance, you just match to that impedance and then conjugate match of a input impedance, and your power amplifier is ready. Okay. So right now this tool does not support non-linearity to be included of the device. Okay, so that is basically something difficult also, because if that thing is included in an open source tool, then itself it will become a, I would say, a paid tool only. Okay, so that will make it as a paid tool only. So, but we are working on it. So maybe soon we will be able to include non-linearities of device in this tool also, so that we can use it for free. But as of now, we have to manage with what we have. But as a matter of fact, but I just want to show you that how a amplifier is designed. So if you are working in a company, or if you are working in a college, or if you are doing a PhD, you can always buy a paid software also. But if you just to start with, just if you want to make the things uh, I would say possible to your guide or maybe to your company. So you can always proof the things with this software, so that you can always do it for free. After that, they will gain the confidence and they can even buy a license for you. Okay, so that's how the things work. Okay, and other thing that that is basically benefit from this tool is that you can always incorporate other dimensions here easily. Okay, so you can always create a I would say a modulated signal and see how your response will change with those modulated signal. Okay, so that things you can always see here. So for that also we are working. But that all those things cannot be covered in one workshop, because this is only 10 days workshop. So maybe next time if we hold a workshop, so we will focus more towards the system design, or maybe towards the non-linearity also, if we are able to add this in this tool. Okay, so we will go to that part also, or if we will get some licenses of some paid tool. Okay, so but as of now, we will focus here only on the conjugate match here. So we will first try it with the LC matching network. Okay, and after that we will so there are many paid softwares available, but for RF design, there are the two most important softwares are the ADS and the microwave office. Okay, so for this RF analog design, these two are the best, ADS and microwave office. So you can use any of that. Okay, so going ahead, right now what we have is basically the same code as what we have designed till now. Okay, so till now we have reached to here. So now to calculate the basically impedance at 5 gigahertz, I have basically sliced the S parameter for a single point at 5 gigahertz. And after that, how the input impedance can be calculated. Basically, you know this formula, right? We know that gamma in is nothing but that gamma in is sorry. We know that gamma in is nothing but the Zin minus Z0 upon Zin plus Z0. Okay, so what you can do is you can take basically this, and this gamma in is now right now what we are assuming it as S11. Okay, because the load we have put right now here is 50 ohm only at the output. Okay, so S11 is that only. So basically, what you can see here is we will get S11 Zin minus S11 Z0 equal to Zin minus Z0. And if you rearrange that, what you will get is basically the Zin equal to S1 plus S11 into Z0 upon 1 minus S1. Right. Sorry, I'll write S11 S11. So you just see the calculation. I might have did some mistake. So this one will be plus. Okay, so this will be plus. Okay, so what we will get here is, so if you just see the calculation. So what I was just want to say is we will get basically a formula of this sort: Z0 upon 1 plus gamma upon 1 minus gamma, or basically ZA. Okay, this gamma is nothing but S11 here, and we have just put here the 1 plus device of S11 and 1 minus S11, and we have got the input impedance here. Okay, so that's how I just wanted to tell from S parameter how to find out the input impedance, and similarly you can find the output impedance too. Okay, so that is how you found the. Okay, so basically this is the input and output impedance that we have got. Okay, so Anupama is asking, can I brief you about designing using ADS? So Anupama, I do not have license to ADS right now, so I cannot teach you ADS here. But if you have license of ADS, so we can always connect and see what is the possible way we can have the session for this ADS. Okay, so for that I think you have to talk to EICT Academy for that. Okay, so that is not come in the scope of this workshop. But because the ADS is a paid software, what we can use only here is the free software that is available. Okay, so coming to the design, we have find out the input impedance of input and output, but we know that these are not the simultaneously matched input impedance and output impedance. So what we have to do is we will start with the output impedance here. So with this input output impedance, if you run that LC matching code that I have provided to you, you will find out that these value will come out. Okay, so just make sure that in that part, what was there is what is what was the what we have done is we have put a ZL here, so that ZL is like this, and we have created a network like this. Okay, and here the Z0 was there, but right now what is our requirement is that our ZL is in this direction. This is our transistor. Okay, so ZL is in this direction right now. Okay, and we need a conjugate of that basically. So we need a ZL conjugate here, and then the network should be there. So if you design this ZL here like this, what you have to do is basically you have to reverse it. Okay, so you have to basically make a mirror image of it. So if by that code your network is coming out like this, then you have to basically connect here in this fashion. Okay, so you have to basically make a mirror image of this thing, so that it basically connects here. Okay, you cannot find it out like this and you just connect it here, the inductor and then the capacitor, then it will fail. Okay, because it suppose that it here it is Z0 and here it is ZL. So what is required here is you have to take a mirror image of that. So basically capacitor will become first part and the second part will become the inductor. And that's what we have done here. If you can see here, so that's what I have done. I have put capacitor first and inductor second, and the values will be the same what we have got. And after that, we have basically connected to the stability device transistor that we have already designed. We have connected the output matching network that we have defined as a OMN variable. After that, I have just sliced down the basically this OMN device to a narrower band of 4.5 to 5.5 gigahertz, so that we can see whether we are able to match it properly or not. And as you can see here, yes, the S22 is basically now matched. It is now basically less than minus 10 dB. Like at 4.9 to 5.1, it is less than minus 10. If it is not less than minus 10, you can always tweak the values here a little bit, so that this response can shift here a little. Basically, what you can do is you can introduce a little mismatch here, so that this response becomes a little broader here. And you can see here, this also the gain has also increased a little bit. Okay, the how the constant E minus and E mentioned across. Okay, so this E minus 9 and E minus 12 is nothing but basically 1.42. The value of inductor is nanohenry, 1.42 nanohenry. That's why I have put E minus 9. So this is another way of putting it. You can always put it like this also. Okay, so you can just put it like this, or what you can do is you can do it like this also. Okay, so there are the two ways of putting it. You can always remove this star and 1 here, and you can just directly put E minus 12 to this value, and this will be like this. Okay. So this is after the output matching network. So Gaurav is saying that S11 should be greater than 10 dB. Yes, Gaurav, you are right. But right now, what we have done is we have just matched the output matching network, and we have not matched input matching. Okay. After this matching, we will do the input matching also, and you will see that yes, we are able to match the output, basically the S11 also to be better than 10 dB. Okay, so after that, what we will do, we will see the input matching network. We will take this impedance and we will design the input matching network also. And this time, this network will be the same. Okay, because now that ZL part will happen. Okay, so you will just connect it at the input of your whatever the device OMN you have designed. You put the IMN input matching network at the input of that device, and what you will get is I have just narrowed down it a little more to 4.8 to 5.2 only. And when you run this thing, you can see here what you are getting is basically S11 and S22 better than minus 10 dB, and S21 is better than 10 dB in our range. Okay, so this is basically the design using the lumped components. Okay, so again we have used inductor here. So obviously we can replace that inductor with a shorted stub anyway. So here also you can just calculate the value of shorted stub instead of inductor, and just replace it with the shorted stub, or and you can use that, and you will see how the response will change, and you can always tune the value of the length of that stub, and you can get the response. Okay, so Gaurav, I think now you can see that S11 is better than 10 dB. So I hope it is now be acceptable to you, that so basically this is our response. This will be our final response. So it will act as an amplifier only, and if you run this, if you basically test it, it will give like power better than, even better than 20 watts also. Okay, so this is, you can see here, this is basically the response of the yes, Aditya, you have to delete buffer.s2p files. Okay, so the buffer that is not provided to you, those S2P file is not required. It was just for me, so that I have confidence that yes, with this software also, if we are designing, it is matching with the measured result. Okay, so you can delete buffer.s2p file, then it will not give error. Okay, so this is basically the design using LC matching. Okay, so instead of LC, you can always put a shorted stub, and for C, you have to put some pads also. And when you include those pads, this response might shift a little, and then you can basically retweak either your pad size, or you can always basically tune your capacitor value also, so that the response will become in your specification. Basically, you will be able to meet your specification using those matches. Okay, as you can see here, our S22 is better than 10 dB from 4.8 to 5.2, and basically our gain can vary from 9 to 11, and it is better than basically 9 I would say 5 in 4.8 to 5.2. So we have enough margin here also, and 5 to 2 S22 also to be compromised, so that this S11 also becomes more better in the range. So as you can see here, it is very close to minus 10 at 5.1. So what you can do is you can compromise on these two responses, so that this will become a little broader. Okay, so that you can do at your end. So that how you will do it. You include those pads also in this thing, so that you will be able to put this capacitor after fabricating. Okay, so that part you will do at your end, and see how the response change. And if the response is changing and your specs is not meeting, then you can always basically tune your capacitor and resistor and all the pad size values, so that this specs is met. So that's how basically a power amplifier is designed. In the next example, I will teach how you can do it with the stub matchings also. But as of now, if any doubt is there, so you can ask me. Otherwise, I'll go ahead with this stub design also. Okay, so if you can give some feedback also at this point of time, whether you have learned something or not, then also it will give me an idea that yes, you are following. Okay, so any negative positive feedback if you want to give, that would be a better. So I'll wait for 2-3 minutes. You can basically think what you can recollect all the things that we have studied till now in today's session. And if anything you want to ask, if anything that is not clear to you, we can take this question. Okay, Sundar, it's nice to hear that it is new, but I would say after that, if you hear anything about PA, it won't find you like what is there in PA. Okay, so now you can tell, now you can discuss with somebody that yes, we can design this thing and that thing. Aditya, basically, I have simultaneously telling how to make the layout only. So we have included all the layout lines in a microstrip format. So you can basically design that layout in any of the layout software so that you can create a Gerber file out of that and print it on a substrate. Okay. So you just have to print all the transmission line that you have included, and you can just print that and put assembly components after fabrication, and it will basically then after that you can test it. In this, can S22 be also possible to make greater than S? It is already greater than 10 dB, right? Gaurav, I think it is already greater than 10 dB, or you are doing something else. It is, I think it is already greater than 10 dB. It is even great. It is very much greater than 10 dB. S22 is very, very good we are getting. It is like, it is almost minus 15 dB in our band. Okay, so somebody is asking that whether fabrication of PCB, can the copper plate be exposed or should be covered? I would say, Akhilesh, the thing is that if there is already the on your substrate, if on your PCB, if it is already covered, the PCB is fully covered with the copper. Okay, then what you will do is you will design this mask. Okay, with this layout you will design this layout. Basically, you will design. So okay, so this is the layout that we have already simulated. Okay, so this layout we have considered in our simulation. So what you will do is you will print it. Okay. So whatever the I would say positive or negative resist that you are having, according to that, you either cover the copper or either you will expose the copper. Okay. So that depends which photoresist you are using. According to that, you will create your mask, and after that, you will basically cover or expose your copper. Okay. So after that, if you basically if you are basically the most common thing is to basically cover the copper and expose the rest part of the copper, so that when you put it into FeCl3 solution, every copper from every place is gone. Only this copper will left. So basically this thing that I am showing to you is nothing but a photo from your PCB only. Okay, so we have just clicked it through some high resolution line. So this is basically, you consider it as PCB. The white part is basically, here also was the copper is there, and what I done is the all the copper has been removed from all the parts. Only this copper that what we have designed as a layout is remain. Okay, everything else will goes off. So now you can basically put your assembly components here, device here, and then you can test it. Okay. Okay. Thank you, Anupama. Thank you. I hope This will help you for designing your PA, whatever research you are doing. It will surely help you in basically give you a kickstart toward your research. Okay. Even I am also basically I use ATS only for my official purposes. But for this, it was asked me to give talk using this software only. Okay, so that's why they have chosen me. Okay, so that's why I'm here. Uh, so that is basically there. Okay, so I think so all the questions have been answered. So there is one question. If I design my PA in GaN technology, but all other components are designed in CMOS technology, then how do we connect these two things together at millimeter wave frequency? The layout that you design for PA is made by assuming PA is off chip, right? Yes, what we are designing is a hybrid MIC that I have already told. But if you are you are right, you cannot design a PA. Basically, you cannot design MMIC with two technologies. That device is from GaN and the component is from CMOS. Okay, so that is not done. It is not possible. You cannot do such designs. You have to choose one technology only. Okay, so in GaN also, you have many, the passive component are easily available on GaN also. So why you want to use CMOS technology for other components? Or maybe which component you are telling, whether you are telling the components like inductor capacitor, or you are saying that that PA is designed in GaN technology and basically LNA is designed in CMOS, then how do we connect to those two things together? So these are basically two different questions. So what is your question? If you can please elaborate. So LA Bethlehem access plus will give more integrations. Okay. So I answer both the questions. Okay. So first question, if I assume your question like that by other circuit components you mean that inductor capacitor and active device is in GaN technology and inductor capacitor in CMOS technology, that is not recommended and it is not possible also. Then it is not also, I would say, recommended to design. But yes, if you are designing the full PA in GaN technology and you are designing your baseband amplifiers in basically CMOS technology, then yes, you can always integrate these two things on a common platform. Okay, so you can use LTCC substrate or something like that. You can basically design LNA, make a chip. You will design PA, that will also be a chip, and then you solder those two things on a common LTCC platform, and then you can connect them with a transmission line. Okay, so two different components you can design in different technology and then integrate it on a LTCC substrate or maybe any other substrate that can work or that with which you have access to. But with these two different technologies, yes, you can integrate like that. I hope I hope the your question belongs to one of this category only. Okay. So thank you, Soham. So we'll go ahead with the basically stub design now. Okay. So it is nothing but the same thing. I'll run it from the top so that we'll not get any error. Okay. So I just run it all the commands first, and now we'll come to our design again. So up till now, the same thing we have done. So now for output matching, we have used a single step match. So at the output, we were having basically the stub here and then a pad and a blocking capacitor after that. Then here we have a pad here. So what we have done is we have done a single step matching here. So for that, what we have done is basically this you can basically use the code also that has been provided to you, or you can do it on a Smith chart also. Okay, so this length you can calculate using Smith chart or using that code. Basically, using that code, you might not get this value. You might get higher value. So you can always. So it will be better if you use a Smith chart. Okay. So that will give you this because in Smith you've seen that in a single step matching, what is there is that there are two possible solution because you can cut your 1 plus jx circle here also and at the other end also. So that optimization, that thing that we are using, maybe you can change the initial guess and it will give you the correct result. Okay, so but I would suggest you guys to do it using Smith chart only. Okay, so that will give you feel also that how the matching is done. Okay, and it will give you, it will basically increase your concept understanding also. So after that, so it will be like a open stuff matching basically we have done. So at this point of time, we just put open stuff here and a transmission line. Okay, so I just forgot that which one comes first. Okay, so basically the transmission line is coming first. Okay, so we have the matching like this here, like this we have. Okay, so after the pad of blocking capacitor, so this is blocking capacitor, we have a pad here. After this pad we have a transmission line. Okay, some delay line is there, and then we have a stub here. Okay, so now after this stub we have to put again a 50 ohm line to put basically connector, because after printing if we want to test it we will have to put a SMA connector, so we will put a 1 mm line also there. So basically this is L9 and this is L10, this is L11 here. Okay, so after just defining all these lines, I have just put it to the our device stability. I have this output matching network. I have just make it in a cascade line, and line 9, line 10, line 11, and I have created an OMN, and again I have sliced down the response so that we can focus on our desired frequency band only. And as you can see, when we run this thing, you will be able to see that yes, we are able to match it. And as you see that we have now implemented through a microstrip line, so our response is it is itself a little broader here. It is not like a narrower response that what we are getting through a that basically that transmission, I would say that inductor part and capacitor. Okay, and this is more real. Okay, so this is more towards reality. And you can see here this is what we have designed here. Okay, so this is basically that 3.2 line, the 3.2 mm line, and this is basically 4 mm 3.9 mm line, and this is that line here. Okay, and after that after designing this you just have to connect it to your output design, output network. So initially we were having up to this stage only. Okay, for bias network, now we have attached the output network also. So this will be our final output, final basically the output stage of the device here. So here will you will have your package only. Okay, so here you will have package, and its pin will rest here like this, and you will put a capacitor here. So that's all on the output side. And basically for basically providing a DC pad, you will make one layout here also, and that will have capacitors. Okay, so this will complete your drain side. Okay, and you will give voltage here. Okay, so DC voltage you will provide here as 28 volts. So this completes your basically output stage. Okay, so your output stage is done here. Okay, so mind you, I have basically tweaked all the values, so that's why you have not to iterate. But it might possible that you have to iterate between output matching network and input matching network a little to get a desired response. Okay, so that might be required at your end. Okay. So after that, I have again calculated the input matching network. So it basically changes our requirement a little. Okay, because we have to do a simultaneous conjugate match. So initially the input matching required was 25.8 plus 45.6, but now it has been changed a little on a J side. And now from 45 it has been changed to 48. It is not much change, but yes, it is a change. So this is I have designed using stub and basically a capacitor. Okay, So now since we have designed everything here, so we at the input side we had a capacitor and a pad here. Okay, from this pad what we have designed, we have put a stub, and again we have put a capacitor here. For those capacitor we have put the pads, and this pad will extend it to, so that a SMA connector will also be placed here. Okay, so this will be your, I would say, the input matching network. Okay, so in input matching network, we have done it through capacitor plus stub matching. Okay, so this what I have told you yesterday also, that it is not like that you just do it with stub only or using lumped components only. You can use the combination of that also. Okay, so here I have used combination. So after that, just we have to create that network. So that's how we have created that network. And after that, once we have created that network, what we have to do is, we just run the code, and you can see here, we are getting some response. It is basically shifted a little, but it is matching. It is giving a good gain at our desired frequency also. And you can see here, the response here of S11 is also a little broader, and S22 is also good. So that's how basically we have achieved the input matching also. And this is basically the layout of the input matching. You can see here, we have a stub here. This stub length is very small, 1.6 mm only, and then a pad here, and we have to connect a capacitor here basically only. Okay, so that will be SMD component. So you have to basically solder that. So you have to put solder here and solder here, so that it connected to these pads. So this will be your final layout. So in which you have a resistor here and a capacitor here. So this will be your resistor, this will be your capacitor. After printing, you just put this resistors and capacitor. This capacitor you will also put here. The device will come. Okay, and its pin will rest here. And here you can see, like, this you have to put the pads. This also you include in your layout, and you have to put resistors here, and then you have to apply. Sorry, so this will be a negative voltage supply. So you have to provide minus 2.8 volts here. So this will be your basically input side, and here you will have, after printing, you will put a SMA connector here. Okay, so you can easily measure this thing. Okay, so this will be your input, I would say, the network of your power amplifier, and this will be your complete layout. Okay, so you can print it on a PCB and put a device in between. So this distance is high right now, but you can always reduce it, so that the device package will just fit into between these two, and it's pinned less on these pads. Okay, so that's how the design is done. And you can see response of a designed amplifier, and you can basically tweak it a little, so that it can comes into our range. And when you fabricate it, you will see that the maximum power it will give, it can give up to like 30 watts. Okay, and the PAE was 45%. So you can see, we have designed a power amplifier here, taking into account all the possible, I would say, possible transmission lines there. That how you can include those transmission lines. What are the effects that you will face after including those transmission lines? So you have to basically tweak those capacitors or maybe pad values, so that your response might get better as you are making, as you go ahead with your design. Okay, so that's all from the design of a power amplifier. If anyone has any doubt, okay, so I can take up here right now. Otherwise, we have time here, so we can, I will teach you one design of combiner also. Okay, so it will take 15 to 25 minutes. I can take. So we will finish by 2:15. So if somebody has any doubt with this flow, if you want to ask anything else also, then we can take up. Otherwise, we will go ahead with the combiner design. So if anyone has any doubt, they just ask me. Like you can ask me right now. Okay, so I think there are no questions. All questions are answered. Uh, I hope my speed is not too fast or maybe too slow for you guys, and you guys think that yes, you have learned a lot of things in this workshop. I would think so. You guys, if any positive or negative feedback you want to give, you can always tell me, or you can even give to EICT Academy also through mails. If you want to give, I would say, a secret feedback also, so that we can improve for later workshops. Okay, so that we can include other things, or if you want to tell that yes, this part or also, so this part can also be covered, that part can also be covered. So for future workshops, we can always plan accordingly. Okay, so because for this workshop, I was just told that we were having a PhD students, max to max PhD students, and maybe some of the faculties that will be in a panelist only. So mainly it will be for the PhD and MTech students, and some PTech students will also be there. Okay, so basically, but what I found during the workshop only, with your doubts and with your mail, some many people have mailed me doubts also. So what I found is that there are many faculty members are also there. Okay, not even from only from NIT Patna. So there are, I think, student or participants from various universities, even from Pondicherry University also we have one participant, one from Karnataka University also, from Meghalaya also. So we have basically, I think we have covered all of the India in this workshop. So it is a huge gathering. So so I think if I have missed some name, or maybe if somebody know if somebody is from middle, maybe from Madhya Pradesh or Bhopal, or maybe from Gujarat, if somebody is there, Rajasthan, if they are there, so you can write that yes, I'm from this university. But yes, we have a variety of participant here. Okay, so we have to take into account the interest of all. So that's why I have, in the first day itself, I've told that it might possible that for some of you guys it might be very trivial, but for the other one, maybe for some other, it is like he is learning just a new thing. So that's why we have tried, so that we start from the basic and we have reached to the design of a power amplifier, and eventually we have actually designed a power amplifier also. So designing a power amplifier, it is not a easy task. Okay, so it is not that easy task. Okay, so Gaurav, you can always connect with me on workshop. Sorry, in on my email, and we can connect with you. So we can talk on this. Whether we can arrange any workshop for that guide how to design PA in ADS. Okay, so that for that you have to uh, uh, drop a email to me, and then we can connect with your college, maybe how we can proceed with that. Okay, so any other suggestions? Okay, so that part I think we can have on validatory section also. So you just make it a point, so that you always give feedback. Okay, whether it is positive, negative, that is not matter. So you should always give constructive feedback. If you find good, you say that yes, it is good, but you can do it better in this way, or something like that. Okay, so I'm very glad, and I'm very I would say I'm very happy that every time I ask for feedback, you guys just make me happy with your appreciations word. Okay, so you getting I always got such a good appreciation. So you guys are very good in appreciating, but I always feel that there is always a room for improvement. So if you can tell that yes, this can be added, or you can do it in that way or this way, so that we can improve for future workshops. Okay, so you just think what can be done, or what all topics that is not covered, if they can be covered in future workshops. So you can just tell those things in your feedback. Okay. So as there are no questions regarding this, so what we do is we quickly see how basically a combiner is designed. So first of all, a little theory of a combiner. What is basically done is, now we have designed a PA here. Okay, what we have designed here is a PA. Now, sometime what is required is to just increase the power. Okay, so now what if we have already designed a PA, what we can do is we can basically we can have two PA and just combine them, so that we so that we have more power. So let's say we have 20 watt power here, so we have 40 watt power here. So if you connect these two things like that, now it won't be like a simple connection that you just short it and you will get 20 plus 20 40. Why is it so? Because what we require here is a impedance here. So we have designed it for a 50 ohm, and other amplifier will also be designed in a 50 ohm. But if you short them and connect a single 50 ohm here, so what you will see here is basically this will become 100 ohm, and this will also become 100 ohm, and this will change the characteristic of your amplifiers. So you cannot just short them like this, or rather I would say it will be it will not be like 100 ohm, or it will be become like, so here it will be a 50 ohm impedance here. Okay, so if you look here, you will see a 50 ohm impedance for a matched amplifier, and if you connect them, so it will become 25 ohm here, but you connect it to a 50 ohm load, so there will be a mismatch here. A lot of mismatch will be here. So either you have to design a matching network here to transfer 25 to 50, or you can design it basically a network, so that if 50-50 will combine, you will get a 50 ohm here itself. Okay, so this is how to do it. Basically, there are many combiners are available. Okay, so I think I can tell you about other combiners in tomorrow's session. But for as of now, the very popular combiner available is the Wilkinson combiner. In that, what is done is, so you can see a topology here in the installation, and basically in this tutorial you can see here we have basically a input path here. Okay, so this is basically an input path, and it will have some requirements of this transmission line, so that it will divide the power equally in both the ports, and the impedance matching will be done. Sorry, basically the impedance will be same at all the ports. Okay, so this will be 50-50-50, and there is a proof of this also, that how it becomes 50-50-50. So for that you have to put a 2Z0 resistor here also. So for to prove this, there is a method called method of symmetry. So you just cut it down in symmetry and see how the things work. So that proof you can find on internet, that how it works. Okay, so just for present session, just consider that there is a network here, of which there will be a 50 ohm line first. Okay, so there will be a 50 ohm line. After that, what you have to do is you have to create a line. Sorry, so you have to basically make a line that is basically a root Z naught, of which the characteristic impedance is root 2 Z naught. So basically the characteristic impedance of this line is root 2 Z naught, and the length is lambda by 4. And again, the other line will also be the same. lambda by 4, and at the end of this line you will connect basically 100 ohm resistance, because we have two Z0, so we will have a 100 ohm resistor here, then again a 50 ohm line here and a 50 ohm line here. So that's how this will work as a I would say as a basically divider here. And if you feed the two powers here, as in our case we have amplifier, so if you feed two powers here, then it will combine these two power and get the output here, and it will be 50-50 and 50 ohm impedances only. So that's how basically the Wilkinson combiner is designed. This is basically a very small theory of Wilkinson combiner, and if you read this tutorial, you will be able to understand the theory, the basically what is required to design. For proof, you can look for the internet. You will able to understand. So there is a reply from here. We have participant from Odisha also. Okay, so that is very good that we have so much of participants here from various states of India. So for this design tutorial, what we have is this specification. So actually, I have thought to discuss this in a very first day session, but the things not go in that sense. But so that does not matter. So we have designed it for 5 to 7 gigahertz specification. You can always change it to 4 to 7, or so that 5 gigahertz will include in this only. Okay. So the return loss, always obviously we want it to be better than 10, but because this is a passive network, so we want it to be even better than 15 dB, so that no reflection occurs. Okay, so insertion loss here means, as you can see here, so basically we are basically dividing the power or either combining the power. So okay, so let's say we basically divides the power. So let's say we have P here. So what will we have here is P by 2 and P by 2. Okay, so basically if we express it in dB, so if it is X dB, so because this is becoming half, so in dB, so basically this power, if it is X dBm, so this will be X minus 3 dBm. Sorry, it will be basically so it will be the same thing we have to write, but in a different form. Only X minus it will be X dBm minus 3 dB. Okay, similarly here also. So basically, so this power will be this will be 3 dB down power. So what you can see here is the insertion loss here will be S21. If this is one port, two port, three port, what you will get as S21 is like ideally it should be minus 3 dB always. Okay, so whatever power is flowing here, whatever power you will get out here will be 3 dB down from this power. Okay, so this is what is the ideal scenario. Okay, but this is a transmission line that is made of a microstrip. Okay, it must have some insertion loss also. Okay, sorry, it will have some loss tangent that will give you some losses. So what is this insertion loss means? That how much the S21 is below this one. So as per it is given 0.5. So your S21 can range from minus 3 to basically minus 3 to minus 3.5 dB. Okay, so 0.5 dB will be the insertion loss. Okay, so this minus 3 dB will anyway come. Okay, but apart from this minus 3 only, you will have some losses. So those loss should not be greater than 0.5. This insertion loss means that. Okay, after that power handling, whatever line you are using, that should be able to handle 10 watts of power. Okay, and the reference impedance is given as 50 ohm. Okay, so if you run this, you just basically go ahead in this tutorial. This was the specification, and we are using Wilkinson power divider, or you can say a combiner for this specification. So it is just written there that equi-amplitude and in-phase signal appear at 2 and 3. Basically, if you feed some signal at port 1, uh, equal amplitude and in-phase signal will appear at port 2 and port 3. And if you feed equi-amplitude and in-phase signal at port 2 and port 3, they will combine, and you will get the combination of that signal at port 1. Okay, so that is basically how it acts as a power divider or as a power combiner. Okay, so this is basically theoretical design that you have. I already told you need a root 2 Z naught line with length as lambda by 4. Okay, so this is basically S parameter of this. This is also I have told that it will have minus 3 dB basically at S21. Okay, so these are S21, S31 or S12, S13. So this value will be 3 dB only. Okay, so if you calculate minus 1 upon root 2 in dBs, so you will be 20 log 1 upon root 2. So that will come as 3 dB basically. Okay, so this is all about our design. So now how to implement in this tool? Again, the same thing. We try it with the ideal components. So you will just define all the components, create a connection, create a network, then check whether the connection is made correct or not. So we can see here that we have a port basically one here. Okay, so this port one, from this port one we have two branches, branch one and branch two, and branch one and branch two, in between that we have a resistor, and after branch two we have a port 2 and a port 3 here. Okay, so if we see the response of this part, what we have is S11 and S22. We can see here they are very much better than like minus 20 dB in the range of basically I would say 4 to 6, basically 4 to even 4 to 7 gigahertz even. Okay, and our S21 and S31 are basically minus 3 dB only. Okay, so they are very close to minus 3 dB. Okay, so now now we have to convert it into basically real component realization. You can read this at your end, that how I have calculated the length. I have already told that you can use this line cal, and after that I have chosen this substrate, and for this substrate you can calculate the width and the length of each line. After that line calculating, you just create those microstrip lines. uh, Okay, so this Wilkinson file is not available to you guys. I will send it to you now. Okay, so I thought to cover it tomorrow, but tomorrow I will I think I will cover switch. I will tell you some theory about switch, not tool part, but how the SPST SPDT switch will be made if LNA is covered earlier. Okay, so tomorrow we have to basically wrap up by 2 because you have quiz from starting from 2:10. Okay, so this file I will share with you guys. Okay, so don't worry about that. Okay, so again the same circuit will be formed. After that, you can see here the same line length we have formed using microchip, but this is a real scenario. This is not ideal, and you will always have a good basically response here, and basically you will have some loss also because of the loss tangent. And if you see separately the S21 value, so the above one will be the real, oh sorry, ideal one, and the below one is the real Wilkinson combiner that we have realized through basically microstrip line. And you can see here it has some variation. So basically it has some loss also. So this minus zero point 0.2 that we are getting apart from minus 3 dB is basically insertion loss of 0.2 dB that we are getting here. Okay, and one more that we can do is that I have created for you guys. Okay, so one question is there. I mean, 3 dB is insertion loss in both port. However, why XDB is coming in port 1 and port 2? In my understanding, it should be X by 2 dB in port 1 and port 2 equal distribution of available input power, which is equal to XDB. So, Wasim, you are right, but what wrong you are saying is that basically in dBs, if you are doing half, basically if you are basically what is happening here is power is getting halved. Okay, so when you are take it in form of dBm, okay, not dB, because power is defined in dBm. So in dBm, half power means 3 dB 3 dB down. Okay, so half power means 3 dB down. Not you will basically divide it by 2. Okay, so division of 2 will be done if the power is mentioned in watts. Okay, so at port 1, if 10 watts is feed, at both the to port 2 and port 3, you will get 5 watts. Okay, so 10 watt is 40 dBm and 5 watt is 37 dBm. So you can see here the power is basically 3 dB down, and not that you divide 40 dBm by 2 and you will get 20 and 20 dBm output. Okay, so in dBm, if you want to represent half power, so you basically subtract it with minus 3 dB. Okay, so that is what is there. Okay, so this was just to create to have you feel of interactive session. Okay, so this was that only. So here you can see we have W and L1. So this W1 and L1 is nothing but that lambda by 4 lines that we have created. So I just wanted to show you guys that it is not that hard and fast rule that you have to choose root to Z naught only. As per your specification, if it allows, you can anyway change those W and L. So root 2 Z naught and lambda by 4 is the value that you have to use for maximum performance. But if your specification allows you, and as per power handling, if your width is for root 2 Z naught is not giving you 10 watts of power handling, so you can always increase the width and decrease the length. As you can see here, we are able to tune our response here. Okay, so S21 is also changing, S11, S22 also changing. So we can always check upon that whether it is meeting our requirement, and we can play around with this width and length. Okay, so that's how we do tuning of our circuits. Okay, so this helps through tool we can have. So through theory we have some solution, but with this we can tune, because for each value we cannot calculate. That is not possible. It will give you much time. So with this tuning part, what you can do is you can see how much variation we can have with the W and L. Okay, so that when we design, we have to basically meet our specification only, and maybe it might be possible that the width for root 2 Z naught for your chosen substrate comes of that value, though that it not be able to handle 10 watt of output power. Okay, so that power that is going to be flow through this circuit. Okay, so you just have to manage that. Okay, so it was just for that. So these two file I'll share with you guys. Okay, I will mail to this to EICT Academy, and they will share with you very soon. Okay, so that's all from today's session. If anyone has any doubt, they can ask me. Otherwise, I will say best of luck for your today's quiz. And if any question is there, you can ask. Otherwise, we will wrap up for today's session. Okay, so we will wait. We will still have 2-3 minutes. 2 minutes we have. The value of reflection coefficient is from 0 to 1, but if it is minus 0.3, any significance of this minus 0.3 is nothing. Basically, reflection coefficient is a complex number. If it is minus 0.3, it is nothing but its phase is negative. So it does not any, it is not of any harm. Okay, so 0 to 1 reflection coefficient your range is because we are considering of magnitude. Okay, so that is basically because the 0 to 1 range is of this thing. Okay, so this thing is basically 0 to 1. So the actual range of gamma will be minus 1 to 1. Okay, so minus 0.3, it's nothing but that the phase is basically greater than 90 degree. So it is nothing to worry. It is just the phase information that is giving with that minus sign. Okay, so any other question if you have? So I am just now I'm sending these two files also. Otherwise I will forget. Okay, so if anyone has any question, they can write. So I will take those questions also. So I think I have answered all the questions. I think Firoza, we can wrap up for the today's session. and I have sent two files
Yeah,
to you. You just upload those files to day 8 material only. Okay, that will include Wilkinson and Wilkinson underscore interactive. So just upload those two files to Drive also.
okay. Did you send me the
Okay.
file in the morning or right now?
Just right now I have sent you. Just right now, 1 minute
Okay,
ago.
okay. Okay, fine. So as soon as I receive the mail, I will upload the content in the Drive. Yeah.
Okay, okay.
Okay. So thank you, participant, for joining with us today. So with this, we will be ending the day 8 session. So we request you all to please join us for the FGP at 2:30 p.m. So we will start the FGP at 2:30 and the link will be closed by 2:50. Tomorrow we will start the session at 10 a.m. I request you all to please join us at time so that we can start the session as per the scheduled time. Thank you, Ashish sir, for the wonderful talk. So by this we will end the
Thank you.
session. Yeah. So all the
Thank you, ma'am.
participants
Thank
have
you.
requested they may disconnect, they may exit the event. We will be ending the event link in 2 minutes. And thank you, Ashish sir. Yeah.